right, we're ready to start this morning. I just wanted to say a few things before we get started. Again, for those of you who may not have been here yesterday, I'm Molly Wagster with the National Institute on Aging. I also want to say that there's apparently a room key card up here on the podium, so if it belongs to any of you, I'll put it right here. You can claim it later. All right, so this morning we have two more sessions today, both of them I think extremely exciting, as exciting as the ones we had yesterday, and so pleased to see all of you back. This session will go until about 10:20, and then we have a fairly brief break, and then we will start with the final session of the summit. We should be winding up around a little after 1 o'clock. So I just wanted to give you all those notes and sort of reminders of how the day is going to go today. Again, we really appreciate everyone being here again and looking forward to very exciting presentations for the rest of the summit. Thank you.
Good morning, everyone. I want to welcome you to Session 5, Comorbidities and Sleep Environment. We have some terrific lineup of speakers this morning. I'm Jennifer Bison from the University of Florida, I should say. And our session this morning is going to start with Gina Poe telling us about sleep features of aging, sleep features and how aging influences them. And then we're going to move to Kristen O'Connell, who's going to talk to us about how genetic environment and sex are important for comorbidities in her research. And then Kristine Yaffe will tell us about the importance of life course approaches to cognitive and brain aging. And then we're going to end with Michelle Mielke, who's going to talk to us about blood-brain biomarkers for Alzheimer's disease and the influence of comorbidities on these biomarkers. So it's going to be a really interesting session, and so I don't take up any more time of the speakers. I'm going to introduce Dr. Gina Poe from the University of California at Los Angeles, and the title of her talk is Sleep Features Impacted by the Aging Environment.
Thank you so much, Jennifer. I am coming off a red-eye flight, so I am the epitome of not sleeping and aging, and so you will see what that does. All right. So this is my grandson. He's 6 months old. You can see at this age on this slide that they're sleeping a lot, and a lot of that sleep is rapid eye movement sleep. But as we get older and older, we get less and less REM sleep, and also, as you can see, when we get very much older, we get a lot less slow wave sleep, and most of this talk is going to be talking about slow wave sleep, even though my research is mostly REM sleep, but slow wave sleep is really important, so we'll talk mostly about that. All right, so here are the stages of sleep. Actually, they're from, this is a Fitbit monitor, which actually isn't terrible in staging sleep, but it's from my sister pictured here, and you can see that is slow wave sleep, that deep blue, big slow waves. The Fitbit and the Apple Watch don't give you EEG, but I drew the EEG on top of it so you can see what this looks like. So we go from wakefulness into N2 sleep and then into deep slow wave sleep. And that is the state that really gets most impacted as we get older. And I'll tell you what that might do to us. Then we go back into N2 sleep, which has sleep spindles, the density of which in any one person is amazingly correlated with IQ. And it is a time when physiologically we are transferring memories from the temporary storehouse in the hippocampus to the cortex. And then we go into rapid eye movement sleep, which is our dream state of sleep, which is what babies have in such high amounts. And in our hippocampus, our learning and memory structure of the hippocampus is a beautiful theta rhythm that's steady and huge. It's much bigger even than you have in wakefulness. And that's another time that's really important for learning and memory. And each of these electrophysiological characteristics have an underlying difference in neurochemical stages. So you can see during wakefulness in that first column, you have lots of acetylcholine in your brain, lots of norepinephrine coming from the locus coeruleus, lots of serotonin. Each of these different neurotransmitters you can see on this slide do different things for learning and memory and cognition. When we go into that deep slow wave sleep state in the next column to the right, you can see the one thing that really stands out is that acetylcholine levels go to zero. And you really need acetylcholine levels to go to zero in the brain in order to set up those slow waves. And in fact, animals that have unihemispheric sleep, the one thing that changes is acetylcholine in the hemisphere that's asleep. It crashes down to nothing. And then we go into that N2 stage with those sleep spindles, you can see, and all the neurotransmitters I have here are down to almost nothing. Serotonin, norepinephrine, and acetylcholine. And this is that unique time when the brain is really shut off to the outside world and transferring memories from the hippocampus to the neocortex. And then we go into REM sleep with tons of acetylcholine, lots of plasticity, and no norepinephrine and serotonin, which are really important to be able to do a bidirectional plasticity, not just strengthening connections between neurons underlying learning, but also weakening connections between neurons that underlines reshaping our brain to accommodate the things that we've learned during the day and refresh our brains to be able to learn new things the next day. So here we're going to go into the functions of slow wave sleep, and this is not my research, but research of dozens of sleep researchers. So what slow wave sleep we know does now is it helps build connections through protein synthesis, which happens uniquely during this state in 10 times the amount that it happens during wakefulness. We clear the garbage through a glymphatic system with those slow waves themselves, clearing the garbage from the buildup of misfolded proteins, et cetera, in the extracellular space that actually gets cleared from the extracellular space. And then we restore our energy. We convert the adenosine that has been built up with the breakdown of ATP. Mitochondria get real busy during this state and build it back up to ATP much faster and much more efficiently than it happens during wakefulness. And it reduces anxiety. And this is the thing we have no idea what the mechanism is yet, but we know that that's actually a really important function. Here is a study by Michelle Krask's lab. Sorry, I don't have the reference on it. But you can see the association between slow wave sleep and anxiety is huge and much bigger than anything else. And in fact, if all you can do is light sleep and dozing, if anything, you have more anxiety at the end of that time. But if you get good, juicy, big, slow wave sleep, your anxiety levels are much, much lower the next day. So here's growth hormone, which is released in a big bolus during slow wave sleep. If we go to bed at a time when our melatonin rhythms are aligned with our sleep, and then you get that in men and women both, you get a big bolus of growth hormone, which is accompanied by a big increase in protein synthesis all over the body, especially the brain. And here's this old slide from 1990 showing that in slow wave sleep, which is at the bottom there, that very dark image at the bottom, there's a cross-section of a rat's brain. You can see that that's the time when amino acids are really incorporated into proteins, whereas wakefulness and REM sleep on the top is really not, it's not as efficient. So here's slow wave sleep cleaning the brain of debris. I liken it to a bilge pump time, when actually with every slow wave, the peaks of slow waves, the cortex is, the neurons are firing, and at the troughs, the neurons are not firing, and it's a very synchronous time of firing and not firing, and every time neurons are firing, they're expanding their membranes a little bit, 15%, and then when they're not firing, they contract again, and all that synchronous expansion and contraction, I think of as a bilge pump, actually. So it's been shown to clear amyloid beta and tau proteins that can cause Alzheimer's disease and other diseases. It happens through the lymphatic system. And really, one of the things I'm going to show you is that one of the things that helps set up these big, deep slow waves is the on and off activity of the locus coeruleus, which is the first area to really degenerate in Alzheimer's disease. It's associated activity of the locus coeruleus, abnormal activity of the locus coeruleus during sleep is associated with stressful conditions and would cause poor sleep, and a positive feedback loop between stress, poor sleep, and anxiety, stress, poor sleep, and anxiety, and also the lack of ability to clear these misfolded proteins. So disturbed sleep and or smaller slow waves really could be a causative factor for dementia. So that's something to keep in mind. So here's an image, unlike the one I showed you before, of a disturbed night's sleep. And unfortunately, way too many of us have a night's sleep like this for whatever reason, and I'll talk about those reasons. So who gets a poor night's sleep? A lot of people get a poor night's sleep. But what happens? So with one of the correlates of a poor night's sleep is aging. Of course, it's variable in different people when they start, their sleep starts aging. But this is an image on the left-hand side of population of older subjects, age 51 to 85, half of whom are female, and it shows that in the red in the front is big, beautiful, juicy slow waves, and there's not very much of that compared to a younger population, ages 18 to 23, which you can see has a lot more red and black, which is the big, large amplitude slow waves, especially in the frontal cortex. And then on the right-hand side, you can see the peak-to-peak amplitude of slow waves goes down. So in gray, the filled gray ones are older individuals, red is female, and gray is male. And you can see that both in females and males, the amplitude of our slow waves decreases as we age. So slow wave sleep also itself is more fragmented, and slow waves themselves are less dense. So altogether, the quality of slow wave sleep goes down with aging, and it's really almost the largest thing that changes about sleep as we get older. So here's showing the duration of slow wave sleep on the left. You can see that the younger subjects are in open circles, and you can see that they have more cumulative probability density of longer duration on the x-axis, slow wave sleep, compared to older individuals, older subjects, which are much less likely to have the longer bouts of slow wave sleep. And then the number of slow waves themselves per minute diminishes with age significantly. All right. So what else could disturb sleep? Well, estrogen. Not estrogen. Actually, estrogen does, okay, well, we'll just talk in a minute. This is what estrous cycle looks like in a rat. You can see all these hormones on the proestrus phase are much higher, and it is not unlike a women's menstrual cycle, where there is a phase when all of our hormones are high. For rats, it's 1 day in every 4. In women, it's more like there's a couple of phases where estrogen rises, but so it's more like less than half of our cycle where the hormones are high. And estrogen itself has effects on hippocampus synaptogenesis, on learning, on LTP itself. And so in and of itself, aside from its effects on sleep, but we did this study a few years ago showing that in that proestrus phase, you can see the females have very, very little REM sleep, especially in the dark cycle. You can see the red line bottoms out in the dark cycle of the proestrus phase, the active cycle in the proestrus phase, and wakefulness increases, and slow wave sleep in purple on the bottom also bottoms out. So these animals are getting much less sleep on this high estrogen phase, especially your REM sleep and slow wave sleep. Well, but the good news is that sleep, the little sleep that they get, is actually way more efficient. You have more spindles per minute, and you have much bigger slow waves. Delta activity is the slow waves of slow wave sleep. And gamma is an accompanying faster frequency. So delta and gamma both increase during that proestrus, high estrogen phase of sleep. So what happens with all the other phases is much lower, unfortunately. And so on this, you can see males are in the open circles, and you can see during this proestrus phase in red, the delta is bigger than males and all the other phases of the cycle. So even though it's little sleep, it's efficient sleep, but all the other phases is less efficient sleep and less efficient than males' sleep. So that's not good either. All right, so what else can disturb sleep? Noisy environments, for example, living in the inner city, helicopter patrolled areas like Los Angeles. It's the most helicopter patrolled city in the world, and I live there, so I can tell you the helicopters do come at all hours of the night, and they fly much lower than the 1,000-foot FAA limit, and circle for 20 minutes at a time. And it's disturbing, and not only is it the noise that disturbs you, but also the threat that it implies. So it is not a good, so on the left bottom orange, that's the flight, that's the biggest, darkest orange is LAX. So that's the noise if you live in the flight path of LAX, and that's Inglewood, predominantly Black and Latino neighborhood, and South LA. Up in the top middle is the decibel arousal threshold. If you just play a 2-second noise at that level, and then overlaid in those colors are how much helicopter circling at 600 to 1,000 feet, how much noise it would make, and whether you have an open window, a single paned glass window that's closed, and a double paned glass window that's closed. And I can also tell you in Los Angeles in the summertime, if you don't have air conditioning, you have those windows open. So that even that can disturb your sleep. Even that deep slow wave sleep, which is usually very hard to disturb someone from, will be disturbed by these helicopters. At the right bottom in the black, you can see in red circles helicopter circling pattern, the flight pattern of helicopters in various like South LA areas. And I'm doing a study together with Nick Shapiro to actually FOIA these helicopter flight patterns and to see what the pattern is relative to the population density and population makeup, and it really is a disturbing picture. Another thing that disturbs sleep, especially as we get older, is obstructive sleep apnea, which gets the incidence of which goes higher and higher, and that is actually a weakening of muscles as we get older. Includes muscles of the airway, and also increasing fat pads that also press on the airway. So the two combine to close off your airway. So even though your diaphragm is trying to inspire, you actually have a closed airway. And to even be diagnosed with obstructive sleep apnea, you have to have at least 5 obstructions per hour of sleep. And that is a lot of wakefulness. And people don't even realize it because the wakefulness, they're so sleepy, they don't even realize they're waking up to breathe, but it is a disturbed sleep. So here's the incidence of sleep apnea that increases with age. And men are more likely to have sleep apnea. As muscles weaken and fatty deposits close the airway, but women also get more and more sleep apnea. They're in the light blue as they age on the x-axis. All right. Oh, and good news is airway exercise, so singing in the shower is good. More airway exercise, more talking and singing you could do, the more patent your airway is going to be at night. So don't criticize anyone for talking or singing all the time. Humming is even a good way to do it, actually. And even people that have a lot of fat that sing opera, because they're practicing 4 hours a day, they do not have sleep apnea. So try that. Or play the didgeridoo. That's another good way to. So another thing that changes with age is the nocturia. So getting up to go to the bathroom at night definitely increases. And so this is the incidence of the population that self-reports their sleep disturbance, the causes for sleep disturbance, and you can see more than 50% of the 55 to 84-year population say they get up at least once per night to go to the bathroom, and that disturbs their sleep more than physical pain or caregiving or health concerns, coughing, whatever it is. Going to the bathroom at night is the number one cause. And it happens in women and men, and this on the x-axis is decades of life. You can see that in women and men, getting up to pee at night is increases, and that was 2 different studies. Yeah. All right. So my time is almost up, but why would this affect memory? Really, that multiple arousals for whatever reason increases the locus coeruleus activity. If your locus coeruleus is becoming hyperactive or hypoactive for any reason, it's a kind of a positive feedback loop and not good. So it changes the molecular and glial supports for learning, your extracellular matrix clearance, all of this stuff. And it's contributed to by stress and the environment, which also tweaks the locus coeruleus and wakes you up. And so this last slide I'm going to leave you with is how to get better slow wave sleep. Increase slow wave amplitude by getting exercise during the day, interestingly, and airway exercise that we talked about before. Make sure your slow wave sleep and your melatonin rhythms are aligned through bright light, and I mean bright light, and try and find a way to reduce the noise and light pollution you experience at night. Maybe it will require policy changes in our society. I want to thank my laboratory and the NIH for the funding throughout the years, and my laboratory, so thank you for your attention.
Thanks so much, Gina. What a great talk. So the next talk is from Kristen O'Connell from the Jackson Laboratory, and the title of her talk is Genetic Interactions with Sex and Environment Shape Sleep and Cognitive Function Across the Lifespan.
Thank you very much. First, I want to thank the organizers, the organizing committee, Molly Wagster, the NIH, for putting this on and inviting me to speak. This has been fantastic. I've learned a ton, and I'm really actually honored to be up here sharing some of our work with you. So hopefully by now you understand that there are a variety of mechanisms that interact to regulate the rate of cognitive aging. And one that's actually incredibly important is that the rate of biological aging, including the rate of cognitive aging, is an interaction between both your chronological age, environmental factors, and your genetic background. Age-related cognitive decline is highly heritable, which means that a lot of the phenotypic variation in cognitive decline with age, it can be attributed to genetic factors. Anywhere from 50 to 80% of that variation is explained by genetic variation. So understanding those interactions and what those genetic factors are can point us in the direction of new targets and new therapeutics to delay or mitigate cognitive decline. But there are a number of challenges to identifying these interactions, both in human populations as well as mouse and model organisms. For humans, we have incredibly complex genomes, and really we have to think of this as a feature, not a bug. We're incredibly diverse, and the way that we interact and respond to our environment and across age is an incredibly important part of why humankind is as diverse and wonderful as it is. We have a long lifespan. That makes us really hard to study for aging, and we are, as a species, notoriously difficult to assess interactions and exposures, particularly across the lifespan. Who remembers early childhood events that happened to them? Almost none of us. We rely very heavily on self-report. And of course, the biggest factor is access to tissue. I think one of the things that we've heard over and over again is that many of the things that are happening during aging that influence where you end up toward the end of your life are occurring in midlife. And in humans, we simply don't have reliable, controlled access to that tissue. Mouse models present an alternative and a solution to some of this. They have a short and very tractable lifespan. We can follow them. They live for about 2 to 2.5 years. We have tremendous control over their environment. We can control almost everything mice do. And we have a lot more precision in assessment and measurement. And of course, they're very tractable. We don't have consent issues with mice, and we can access brain tissue at any age. However, there's one major drawback that has influenced the translation of data from mouse models to human, and that is genetic background. Most of our mouse models that are in common use are a single genetic background on an inbred strain. It's most often C57 black 6, most often male. So there is one of these things that is a modifiable factor, and that is the genome of mice. And most of the work I'm about to tell you about represents a very long collaboration with the Kazarowski lab, who presented some of this yesterday, so I won't belabor it, except to explain that we've taken the BXD panel that she referred to yesterday and extended it and created an F1 panel, which introduces a few advantages, including introducing a considerable amount of genetic variation. The BXD panel now carries about 6 million genetic variants across upwards of 140 strains. We've created 60 of these F1 lines, give or take. And by creating an F1 panel, we introduce heterozygosity. So we have a mouse panel that has some variation in allele frequency at each allele. I also won't belabor how we assess cognitive function in mice, but we've heard this, except to point out that most of what I'm going to describe can be described as pseudo-longitudinal studies. We phenotype our mice at age-based cohorts, so we can assess them repeatedly through the lifespan and collect tissue at each one of those time points for downstream molecular analysis. So what does this do to cognition just by introducing genetic variation? What does this do to cognition in the F1 BXD panel? So just to orient you to this slide, you'll see this pattern on a number of my slides. So this is contextual fear memory. This is day 2 of the CFC task, stratified by sex, so males and females. Females and males if you're looking at me. Each point represents a strain average. So this is one individual BXD strain and the average of all the mice from that strain per age from 6, 14, and 22 months of age. And of course, the box plots are box plots. These are the population averages. Hopefully, the thing you'll notice is that the biggest determinant of cognitive function at every age is genetic background. Strain explains most of this variation, not age and not sex. We have strains that perform exceptionally well at young ages and through the lifespan. We also have strains that don't perform well, even at young ages. And this actually parallels the human population much better than using a single strain does. The other significant thing is that there's a profound sex difference here. And we heard this a few times yesterday, that often males and females start at the same place and they end in the same place. It's the trajectory of how they get there that's different, and that's true in our panel as well. Females start high at 6 months, and they maintain that into midlife. 14 months of age is late midlife in mice. And then they decline from midlife to old age, and 22 months is truly old for a mouse. Males, on the other hand, start high, decline in mid-age, and then maintain that into late life. So they end up at the same place, and they begin at the same place, but how they get there is different. And of course, like humans, we have a survival bias. More of our female mice survive to 22 months of age than the male mice do, so female mice are overrepresented at 22 months of age, and this is actually strain specific. We have strains in which no males survive to 22 months of age. So Dr. Poe has already done a much better job of explaining sleep and cognition and their relationship than I can. So the main thing that I want you to take away, and this is the whole theme of my talk, is that there are individual differences in phenotype in and of itself, and it interacts with age and cognition to influence behavior. Sleep patterns are highly heritable. About 50% of the individual differences in how we all sleep can be attributed to genetic variation. So now that we have a population of mice with that genetic variation that approximates what we see in humans, what does sleep look like? And in fact, not surprisingly, genetic background is the most significant influence on sleep patterns in mice. So this is total sleep per cycle, so light cycle, dark cycle. We all remember that mice are nocturnal, so they sleep the most when the lights are on. But there's a huge amount of variation, so each one of these box plots is the percent sleep during that cycle for a given strain. Some strains will sleep almost 70% of the time during the light cycle. Others, less than 60% of their time is spent asleep. And we see just as much, if not a little bit more variation during the dark cycle, where some strains will spend almost 40% of that cycle asleep, others less than 20 or 15. And just so you know, this equates to about 2.5 hours of difference across the panel. So we just have some mice that are genetically tend to be short sleepers and some that tend to be long sleepers. One of the other big factors that was alluded to in Gina's talk is that, there we go, things like obesity and body weight influence sleep. They also influence cognition. And understanding how obesity and diet and these sort of environmental factors and lifestyle factors impact neuronal function and plasticity has been an interest of my lab for quite a while. There is an association between sleep and BMI. I think most of us probably know this, that increased BMI is associated with short sleep. Short sleep is associated with increased BMI. Causality between those things is still not known. The consumption of obesogenic diets in animal models leads to sleep disruption and circadian dysfunction. And to sort of follow on a theme from yesterday, the brain is not an island. It does not function alone. It's connected to the rest of the body. And obesity and high-fat diet consumption uncouple peripheral metabolic pathways from the central circadian clock. And so all of this combined is associated with increased risk for cognitive impairment. So how do we integrate all of these things to study all of these factors, genetic background, age, sex, and diet, and sleep? Because that approximates the human condition the best. So we're using a very well-validated and characterized model of diet-induced obesity in mice where we feed them a high-fat, high-sugar diet. This is a model of a Western diet. We start them on the diet. They're randomly assigned to either control or high-fat diet at about 3 months of age, so it's fairly young. And then we monitor their body weight and phenotypes throughout the lifespan. Again, this is a pseudo-longitudinal study. These mice get additional deep metabolic phenotyping. We put them in these fancy cages, which give us incredibly deep and rich metabolic phenotypes, 24-hour continuous monitoring of metabolism and behavior, from which we can extract sleep and circadian-related behaviors. I will concede that this is not the gold standard for these assessments, but it actually does a really good job of approximating this in a way that's amenable to high-throughput screening of thousands of mice. So this is just a proof of concept. This model works really well at inducing obesity, particularly in male mice, which is, of course, the model in which it was developed. There is variation in body size dependent on strain, and again, strain and genetic background explain most of the variance here. Male mice respond really well to a high-fat diet. Most mice, most strains will gain weight on a high-fat diet, and this is dependent on age, where it gets bigger as they age. Female mice are similar, except that, again, it's delayed. They get to the same place, but the trajectory is different. It takes a little bit longer for female mice to gain weight and become obese. But again, genetic background is the biggest driver here. Surprisingly, it is not diet. It is genetic background. So it is response of individual genetic variation to that environmental factor that determines whether or not an animal will become obese, and this is likely true for humans as well. So what about sleep? What happens if we look at sleep in these mice that are on a high-fat diet and are either obese or not? Again, I know I sound like a broken record. Genetic variation explains most of the differences that we see here. And this is actually really profound for this particular phenotype. In male mice, it explains 3/4 of the phenotypic variation. And there's, again, a huge sex difference between how males and females respond across age and to a high-fat diet for their sleep patterns. Male mice, and I do want to point out this is only dark cycle sleep because there was no effect of diet or sex on the light cycle, only genetic background. The dark cycle is much more variable. Male mice respond to age and diet, so there is an effect of diet in old males. They tend to sleep during the dark cycle, and they trend, actually it's a significant decrease in their total sleep during the dark cycle with age. Females are completely different. There's actually no effect of sex or of diet. Being on a high-fat diet or being obese doesn't influence their sleep, and they respond by sleeping more, not less. So if you're going to anthropomorphize them, this would be analogous maybe to a human having increased daytime napping, because the dark cycle is the active period for mice. I'm actually going to, so this is circadian. We used food intake as a proxy for circadian disruption. And again, just to prove the point, genetic background is the biggest driver. diet plays a big impact here, and as I said, that circadian disruption is common in obesity. This is also strongly sexually dimorphic. It happens very early in males, and by late life, they kind of lose that circadian patterning to food intake. Females maintain it for much longer, but again, it's the trajectory that's different, not the destination. So what we're really interested in, though, in my lab, is making this link. How do we get from this genetic variation and all these interactions to our ultimate behavioral phenotypic outcome? And a lot of what's here in the middle is unknown. There's a lot to fill in this gap. And again, to kind of refer back to the comments that were made yesterday about how much technology has kind of come, how far it's come in the last 10 years, we now have the ability to do very deep, very detailed omics measurements in a way that we couldn't do even 5 years ago. And so taking advantage of, there we go, some of the resources available at JAX, where we have a really sophisticated mass spectrometry and protein sciences core. And we now have the ability to do mass spec imaging, which is a new technology that didn't really exist 5 years ago. And this is our workflow and pipeline for mass spec imaging. To kind of condense this, you can think of this as basically you take a brain, you prep it for histology, but instead of using a microscope to image it, we're going to spray it with matrix and run it through a mass spectrometer. And we use the Bruker timsTOF Flex platform to do this, which is really optimized for MSI. We have a whole platform to extract those spectra, convert them into features, and annotate them. And this allows us to profile in an unbiased way lipid, metabolite, and peptide composition and abundance with high levels of spatial resolution across the brain. This is just an example of what this looks like. So it actually doesn't look that different once we get done processing it from a microscopy image. So we have anatomical and structural information. I do want to point out that there is no actual anatomical or structural information in this image. This is lipid abundance. And it looks like a heat map, but it's actually a PCA. This is a high dimension PCA plot. The colors are lipids that are most similar to one another compared to the entire brain. So the outer cortical layer is more similar to itself than it is to the rest of the brain, and you can make that comparison for everything. This is a brain from either a lean, normal chow, low-fat diet-fed control, or a mouse that's been on a high-fat diet. And these were processed and scanned at the same time, so you can make direct comparisons between these two images. They are normalized to one another. So this is just changes in lipid composition with respect to the entire brain, but we can do ROI segmentation and drill down onto specific regions. And since we're interested in cognition here at this meeting, we did this for the dorsal hippocampus. And so now you're looking at lipid composition relative to the entire hippocampus. And again, there's no actual spatial anatomical information here. This is all lipid abundance. So there is a tremendous variation in lipid abundance across the hippocampus. And we can take this image, which effectively represents every single feature that we can acquire on the mass spec, and there are over 3,000 of them, and collapses it into a single image, which is really hard to process and interpret. So we took a few of those features, a few of the named lipid classes, and we can now superimpose those onto onto this image, onto the brain, and look more specifically at specific classes of lipids. So this is 9 of our most differentially abundant lipid classes. Now what you're looking at are real differences in abundance across the brain. Colors are individual classes of lipids. I apologize, once you get up to 9, you start running out of colors. So there's a lot of the same color on here, but hopefully it kind of drives home the point that even after just a few months of eating a high-fat diet, the lipid composition throughout the entire brain has begun to change. And these are actually genetically identical mice, so this is really a diet-driven effect. And I also want to point out that you may not be able to read this on the slide. The lipids that I'm showing are both important for membrane structure and fluidity, but they're also bioactive signaling lipids. Choline, phosphatidylinositol, ceramides, sphingolipids. These are really important lipids for the function of the brain, and they are changing in response to diet. And so just to wrap up, hopefully I have convinced you that by increasing the genetic diversity of our mouse models, we can actually do a much better job of aligning these models to the variation across the human population and do a better job of capturing that diversity both genetically and phenotypically. And that we can take this and now make it a model to capture some of the complexity in just the lifetime exposures of humans and start to model that and model those interactions and better understand what the underlying genetic and molecular drivers of those responses are, to do a better job of understanding how we age in every facet. And then our goal is to now use these advanced multiomics to start filling in these gaps. How do we get from genetic diversity to phenotypic diversity? What are the actual effectors at levels we have previously not really been able to assess, like the lipidome, the metabolome, and the peptidome? And then finally, there are a large number of people involved in carrying out a study like this. So I want to thank members of my lab, including Amy Dunn, who's a research scientist, who actually led that entire obesity study and worked with an intern, Miko Dai, who organized all of the data. For those of you working with big data sets, you know how important it is to have good curation, cleaning, organization of your data, and Miko left that data set in a fantastic condition before she left to go to graduate school. This is a collaboration with the Kazarowski Lab. It's an ongoing collaboration that we're all very excited about. And then, of course, to thank the funding agencies that have supported this work for so long, including the NIA. And also really need to thank the Protein Sciences Core and my collaborator, Brian Hoffman, who's working on all of the mass spec imaging and proteomics. So thank you very much.
Thanks so much, Kristen. That was awesome. So the next talk is going to be from Kristine Yaffe from the University of California, San Francisco. And the title of her talk is Importance of a Life Course Approach to Cognitive and Brain Aging.
Hello, good morning. It's really a pleasure to be here. I want to thank the NIH, Molly and Jonathan in particular, and the McKnight Foundation. This has really been a lot of fun. I think what you hear is sort of what we all try and do, which is learn from one another, meet new friends, and I love the translational aspect. You know, the fact that we're talking about mice, we're talking about people. I'm going to talk about people, although it makes me think, based on the prior talks, maybe I should switch to mice. So I'm going to talk about two things, really. One, you heard a little bit about the life course. I'm going to try and convince you why I think a life course approach to cognitive aging is very important. And then I'm going to talk a little bit about some recent work we have from a trial trying to improve cognitive aging. Oops. What am I doing wrong here? It's not the right side. There we go. Okay. So we all know that the physiologic and neuropathologic changes that happen over age take a long time to develop. And so, we think decades, right? We also know there are a lot of risk factors that may lead to cognitive aging and dementia, such as vascular changes, sleep, which we've beautifully heard about, physical activity. And yet, most of our work has really focused on older adults, people in their 60s, 70s, 80s, and I would like to hypothesize that we're missing really a chance to understand the whole life course and what's been happening before, maybe even starting in utero. So it's hard to study this, though, right? We're not mice, and in humans, we don't have studies that go for NIH cycles or 5 years, and I know Molly's working on that, but, we don't have an NIH study that's 80 years old. So it's hard to study this, and yet we're missing, I think, this opportunity to study people for decades and their whole life. We don't have birth cohorts in this country. Some countries do. This is sort of this idea in a figure. And the other thing is that these risk factors may be cumulative. So you might have, obesity for 50 years, and that may be very different than somebody who gets obesity when they're 70, or hypertension, for example. There may be critical windows of exposure, for example, with hormones. It might be very important whether you get hormones around the perimenopause or whether you get hormones started much later. So these are some examples of why the life course is very important. Again, I said it's hard to study this because we don't have a lot of these. You can do pooling of cohorts, which we and others have done. You can do some analytic methods. You can use Mendelian randomization is a great way to go, et cetera. But I want to show you a study that we've been involved with called the Cardia study. And this is a really great study I want to increase your awareness of, because I think it provides a lot of opportunity. It's an NHLBI-funded study. What's really cool about this study is this is a study of 5,000 people, half women, half men, half black, half white. So pretty diverse. And we have been studying them now for almost 40 years. They started when they were in their 20s. So the mean age when they started was about 25. It's a little hard to see this, I'm sorry, but you can see the boxes represent each visit, and then that's the mean age, what they were. So they started when they were 25, and then when they were about 50, we started doing cognitive and brain MRI assessments, and that's been sort of my role with some colleagues. And we're now coming up to the point where they're actually they're in their 60s, they're mid-60s. So it's a really great opportunity. I'm going to show you some of this work that we've been working on since when they were 50, using the cognitive and brain MRI. And really our goal is to try and understand this life course approach. How do these cumulative or life exposures that often are modifiable influence cognitive aging when people are in midlife? And what we're hoping is as the cohort gets older, that we can continue to study them. We just submitted a renewal to study them when they're 65. And I'm going to focus on just a couple examples just to give you a flavor of why I think this can be so powerful. Okay, so the first example is blood pressure. Now, we know that blood pressure is extremely important for risk of cognitive aging, dementia, not to mention stroke and MI, et cetera. This is some work we did a while ago where we said, okay, what's the blood pressure exposure from when people were in their mid-20s now to all the way to 50s? And these were not people who had hypertension, so they did not meet the criteria for hypertension. It was just their blood pressure. And we looked at their systolic blood pressure, and then we did this AUC, area under the curve analysis, which is kind of a acute use of the AUC to look at a cumulative exposure. And what you can see pretty clearly is that the lines are all the cognitive tests. You can see that the greater exposure, if you will, to high normal systolic blood pressure, the worse people did on their cognitive function. So really compelling to think that even if you're sort of high normal, and you're high normal for many years, this might not be such a good thing. And we saw this for other cardiovascular risk factors as well. Recently, Christina Dentinka, a postdoc in my group, did some beautiful work looking at brain aging. So what she did was another way to look at systolic blood pressure exposure and diastolic blood pressure using a time-weighted average. So taking, again, from mid-20s to 50, 55, and what she found was using a machine learning brain aging pattern that Mohammed Habas developed. What she found was that if you have higher systolic blood pressure for all that time, or diastolic blood pressure, you have a greater brain aging. So that the red line is if you're elevated above the cutoff, and the green is sort of normal. So showing, again, there's something going on with brain aging pattern. This is not white matter. This is just sort of an atrophy pattern. Oops. Okay. And we've also done some work looking at actually having these cardiovascular risk factors, so diabetes, blood pressure, cutoffs of hypertension, et cetera. And we found that having this in midlife, having this when you're 50, was associated with accelerated cognitive decline. So again, we think cardiovascular risk factors very important starting in one's 20s. What about depression? This is something I don't think we've studied enough as a field. What's going on with depression and cognition? I think it's extremely important. This is some other work Christina Dintinka has done. She used latent class analysis to develop these different, to look at patterns. And as you'd expect, most people don't have a lot of depressive symptoms. This is repeated depressive symptoms over 20 years. But there are some people who have declining, some people increasing, and some people who stay high and remain high. And then what she did was she looked at how do these different patterns relate to cognitive function. Again, when the people are in their, this is middle age, 55. And how did it vary in terms of MRI findings? Compared to those who are always low, those who are in the different groups, higher, always high, increasing, decreasing, had worse cognitive function. This is on a composite cognitive measure. And they had differences in terms of entorhinal cortex volume and also amygdala volume. So this was looking at the high group compared to the low group. And then compared to the increasing group compared to the low group, they also had differences, but in this case it was more white matter and total gray matter volume. So I'm now going to turn to, I'm having trouble with this. There we go. Sleep. The last thing I want to show you is sleep, which we've beautifully heard about today. This is some work that Yu Lang has done in my group, some beautiful work looking at sleep quality. Again, this is when people were about 40, and then showing that the cognitive function 11 years later was much worse on a variety of sleep parameters. We heard about fragmentation, wake after sleep onset, so you're tossing and turning, lying there, subjective ratings, or sleep apnea. And this is some other work we did looking at sleep, in this case duration, showing that differences in sleep duration, short sleep duration in this case was associated with worse white matter quality in terms of DTI and also actual white matter volume. So I hope I've shown you that there's really good evidence that looking at some of these risk factors earlier in life might be very important in terms of cognitive function at midlife. And I would tell you, I think this sets us up. I mean, we've heard a lot. We can't pick our parents, and we can't do much about the genetics, but we can do something about some of these things. And maybe we're starting too late. I think they operate really early, and if we want to try and set us up for a better trajectory of cognitive function and aging, we need to really start looking at this earlier. Probably trying to do some sort of multi-domain risk reduction. I had an interesting breakfast conversation about this very thing. I'm going to show you some work we've done looking at this. So we got very interested in, well, what if you could move the needle on some of these risk factors? What if you could modify some of these risk factors? And this is work we did quite a while ago with Deb Barnes and myself, where it was sort of a thought experiment. If you could actually move the needle, what could you do? And so what we first did was we calculated the population attributable risk of some of these risk factors. We looked at 7. Some were midlife, some were late life. And we thought about 30% of the population attributable risk for dementia and cognitive aging would be related to some of these factors. And then what would happen if you could reduce them? And you can see in the red and the blue, this was 10% or 20%. So you're not even asking people to, exercise like join a triathlon. You're just asking them to change their behavior 10%, 20%. And you could see that as a public health person, you could have a big downstream effect on dementia prevalence, and I would posit cognitive aging trajectories as well. The Lancet Commission has sort of replicated this work, and they've expanded now to 12 risk factors, and they say now that it's about 40% of the variance could be explained. I'm actually not sure some of these risk factors have been so carefully studied, but the idea here remains, this idea that if you can change some of these risk factors, you actually could improve cognition and reduce dementia. So that's all great, but how do you get people to change their behavior? It's not so easy. The NIH has been very interested in this. NIH had a great workshop with National Academy of Medicine, and ARP has gotten very interested in this. How do you get people to change their behavior? I know I should exercise more and eat better, and I'm not bad about it, but it's hard to get motivated. So we were really interested, how can you motivate people? How can you get people to engage in risk reduction? So we decided we were going to do a trial and make this personalized. One of our themes of this conference is precision medicine. This was our precision medicine in terms of reducing risk factors. So we designed this trial. This was funded by the NIA. Thank you, NIA, and Christina McLinden is our project officer. We did a multi-domain risk reduction trial. This is with colleagues at Kaiser in Seattle. And what we first did was we said, okay, let's identify people who have risk factors. So these were people, they did not have dementia. They were older. They were 70 and above, because we wanted to see if we could see cognitive change in a short amount of time. But they had to have at least 2 risk factors, and we got these from EHR using the Kaiser data. And then we said, okay, we had a list of 8 risk factors that they had to have, and 2 or more of those. And then we said, all right, we're going to do half of them will get controlled. They'll get education. We sent them materials from the Alzheimer's Association, et cetera, on the same risk factor. Other ones had a personalized intervention. They got to choose what they wanted to work on. So we told them what their risk factors were, and they said, okay, I want to work on physical activity, or I want to work on my sleep. I want to work on my hypertension. And so we engaged them by them choosing what they wanted to work on, what they had, first of all, right? And then what they wanted to work on and how they wanted to work on it. Do you want to go to the gym? Do you want to have a Fitbit? Do you want to do CBT for insomnia? What do you want to do? And then our outcomes were cognitive function, of course, looking at the risk factors, changes, and quality of life. We had much more risk outcomes, but this happened, we were finishing enrollment in March of 2020. And this was Seattle, which was the first city to shut down. So, just my luck, right? Anyway, it was very interesting. But in the end, we ended up going all remote, which in some ways made it more practical. So this is what we found. We found after 2 years, the cognitive composite actually, this was a cognitive composite that was a modified neuro test battery, very similar to what was used in Finger. And to our absolute delight and frankly my surprise, because this was all during COVID, what we found was that the intervention group actually improved, both groups improved. And many primary prevention trials have found that the cognitive function improves. So we found that both groups improved, but the intervention group improved much more, about 80% more than the control group. And you can see this was pretty sustained. This was an average treatment effect of 0.15 standard deviation, which is very similar to a lot of drugs, maybe even better than some drugs. So we're very excited about these results. And of course, we looked at the risk factors. So, did the risk factors change? And this was a secondary outcome, and of course, the risk factors did change. Now, you see, they didn't change so much in the beginning, the first 6 months. Well, that was when COVID hit. So the first 6 months were, probably middle of 2020. And but the intervention group actually stayed the same. The others the control group got worse. And then you can see they sort of rebounded. And there was an improvement in quality of life, again, statistically significant across the 2 groups. So we're very excited about this. We're interested in sort of taking this to the next step, probably doing a bigger multi-site trial. But I also think we need to be thinking a bit about, should we be doing this in midlife? It's something we were talking about this morning, because I think, is late life too late? It's hard to study people in midlife. You're not going to see as much cognitive change, but you could, I think you could look at cardiovascular outcomes as well. I hope I've shown you that the importance of the life course, that these risk factors are operating over our whole lives, and again, probably even earlier than we can study in terms of early, childhood and in utero. But I think we need to understand this much better. How does this set us up? I'd love to, partner with Kristen, and how can you look at, maybe you use the mice to find things and then you roll it out into people, or I don't know. But I think there's some really cool things you could do in terms of improving your cognitive, this is all what we talk about with risk and resilience, really. How do you get the brain to be resilient? How do you reduce risk? I think we need much more research on diverse populations. This cardia is somewhat diverse, but I think we can do better. And really, I think starting to engage more in community participatory research. We've done some work looking at diverse participants and seeing, the risk factor profiles are very different, and particularly at recent immigrants or different places in the country. So I think we need to pay attention to that. Ultimately, I think these sort of personalized approaches might be much more effective. You get buy-in from the participants, and you're meeting them where they are. So I think, but for now, I think we do have some recommended things we can offer to people. They're low cost. They don't have a lot of side effects, such things as cardiovascular risk modification, sleep, hygiene, for example, physical activity, depression, of course. That involves usually more of a practitioner approach. So I want to thank you. This is my group and some of the funding that I showed today. So thank you so much.
Thanks so much. Such great data. Okay, so our last speaker is Michelle Mielke from Wake Forest University, and the title of her talk is Interpreting Blood-Based Alzheimer's Disease Biomarkers, Impact of Comorbidities.
Well, thank you very much, Dr. Bison, and thanks to the organizers for the opportunity to talk here today, and also to put us in this lovely group, which, if you can see, we're all color coordinated. But it's been a lot of fun. So really difficult to follow all these great women. My talk is going to veer a little bit with more focus on blood-based biomarkers and thinking about how to interpret them in cognitive aging studies. These are my disclosures. So, the development of ways to assess in vivo pathology, including Alzheimer's pathology, has really changed the course of our understanding of the impact and influence on cognitive processes. Of course, initially there was amyloid, or there was PET, as well as lumbar punctures for CSF, but there's a lot of disadvantages to them, both clinically and in terms of research, in terms of cost, potential limitations, and accessibility, as well as invasiveness. So the technological advances that have led to the development of blood-based biomarkers for Alzheimer's disease really over the past roughly 5 years have been an incredible accomplishment. Some of these markers are now available for clinical use, and in fact some of the immunoassays are reimbursable through CPT codes. However, most studies to date, typical when you develop biomarker studies, have focused on very well-characterized individuals in specialized clinic populations. And so there's still an overall lack of understanding as to how these markers work in the general population, as well as what factors may interpret their levels in the population. So in the rest of these slides, first I'm going to talk about the potential impact of comorbidities and medication on the levels and considerations when interpreting these biomarkers. And then I have a couple more slides thinking about how to analyze the data and think about it potentially in some of the clinical epidemiological studies in which you may be working on. So originally when we were first thinking about how to interpret these markers in the population, we were looking in the Mayo Clinic Study of Aging, which is a population-based study of older participants in Olmsted County, Minnesota. And here in this particular slide, we look at plasma p-tau 181 and 217. The results are essentially the same, so I'm primarily going to be focusing on p-tau 217. The black includes unadjusted analysis, and the red adjusts for age and sex. And to give you a baseline comparison, we see on the bottom, this is the difference in plasma p-tau measures between individuals who are amyloid PET positive versus amyloid PET negative. So if you look at p-tau 217, you see there's about a 0.7 difference. Now, interestingly, when we started to look at a variety of comorbidities, Particularly with chronic kidney disease, you can see that the difference between somebody with versus without chronic kidney disease is basically the same as somebody with versus without elevated amyloid based on amyloid PET. And this isn't driven by amyloid pathology, because even if we exclude those individuals that are amyloid positive, we still see this very striking difference. Now, in addition to CKD, we also found elevated levels of plasma p-tau for individuals who had a history of stroke as well as a history of myocardial infarction. In additional work, amyloid beta as well as NFL and GFAP, and this figure shows you amyloid beta 42 and 40 as well as the 42 to 40 ratio. And again, if we focus on CKD, we see higher levels for amyloid beta 42 as well as amyloid beta 40. However, when we do look at the 42 to 40 ratios, some of that difference is attenuated. And so really, in this chart, the red is cognitively unimpaired, and we only saw that difference among cognitively unimpaired individuals. So there's been many studies that have replicated the finding with CKD and higher levels of these blood biomarkers since that original study. But I think it's important to point out that there's actually a relationship across the range of kidney function. So if we think about CKD, that's generally eGFR lower than 90. But as you can see with this particular study, even though there's a very significant correlation between eGFR, NFL, and GFAP, even for those individuals within the normal range of eGFR. So physiological functioning of the kidney certainly impacts the levels of these biomarkers. Now, there are studies that adjust for chronic kidney disease, and it really doesn't make a difference when you're looking at the relationship between these biomarkers and cognition. In a couple slides, I'm going to talk a little bit more about that and why that might be. But most of the studies, when you think about they're group studies when you're adjusting for CKD. How does this actually affect individuals on a basis in terms of diagnosis? And so this really became apparent to us. I was working with Melissa Murray at Mayo Jacksonville, where we were looking at the correlations between the plasma biomarkers and neuropathology. And interestingly, what we found was that this person that had the highest plasma p-tau really had moderate amyloid pathology, but very low tau pathology. So essentially, they had the highest p-tau level and potentially would have been diagnosed with Alzheimer's disease, but actually didn't really have significant Alzheimer's pathology in their brain. And what we found for this person was roughly 2 weeks before they had their blood draw for our study visit, they had a creatinine level of 3.7. And so again, if this person came into the clinic without recognizing that chronic kidney disease has an effect, could have been diagnosed with Alzheimer's disease when in fact they really didn't have the brain pathology. There has been some work trying to figure out how to mitigate some of these effects and interpret these biomarkers for individuals that have chronic kidney disease. This work does highlight, again, similar with amyloid beta, when we use the 42 to 40 ratio, some of that effect was attenuated. And this work also highlights when you look at the phosphorylated p-tau 217 to 217 ratio, some of these effects are highlighted or are attenuated as well. Now, this particular study had focused more on mild CKD patients. So there is ongoing work by Carrie Sheets and Murray at the Berman Institute who are looking at these markers and potential ratios also in moderate and more severe CKD. So shifting gears just a little bit, I just showed you this figure. What I didn't highlight at the time was the inverse association between the levels of these markers and BMI. So with increasing BMI, we actually see decreasing levels of the plasma p-tau markers. And this has been also found in other studies, as you can see here in BioFinder, where you see the same things with plasma p-tau as well as NFL and GFAP. Now, what might be the reason for this explanation? The first study that really focused on this came out in 2020 looking at MS patients and controls. And they found that there was an inverse association between body weight and NFL, and that this was driven by changes in blood volume. So with increasing obesity, there's also increasing blood volume, and that this is resulting in lower levels of NFL. Importantly, again, obesity or BMI in these patients did not change the relationship, it did not affect CSF NFL levels. So this is certainly a peripheral phenomenon. And I think this highlights even more what the potential effect of BMI can be. So the study by Draelos had looked at NFL and GFAP levels in normal weight patients, or normal weight patients, and compared them to individuals who were overweight and about to undergo gastric bypass surgery. And I don't think I have a pointer here, but what you can see is that individuals who were of normal weight had higher levels of NFL compared to those individuals who were obese. However, interestingly, 6 months later, when individuals went from an average BMI of 41 after gastric bypass, you can see that the elevated, that NFL and GFAP are elevated, and that there's actually no difference anymore between the normal weight individuals and mildly overweight individuals. And I should mention, too, because I've talked quite a bit with some of our weight management physicians that are in our department, and typically with gastric bypass surgery, you see a better actually increase in cognition. So you wouldn't expect there to be a decrease in cognition or changes in adverse changes in neurodegeneration. In addition, there's also more work suggesting that blood amyloid may be affected by cardiac conditions. We know that amyloid beta accumulates in the heart of Alzheimer's patients and induces AD-related cardiac amyloidosis. And some recent studies have shown that plasma levels of amyloid beta 40 and 42, high levels, are risk factors for heart failure and other cardiac conditions. Now, a recent study that came out in JAMA Neurology also showed that Entresto, which is sacubitril, lowers the plasma amyloid beta 42 to 40 ratio, but not the CSF 42 to 40 ratio. So you can see here in the left two columns that this particular medication increases levels of amyloid beta 40 and amyloid beta 42 over a period of a year. However, interestingly, the ratio is significantly increased in these individuals. So again, this is a possibility without this knowledge of somebody coming in on this drug. Low amyloid beta 42 to 40 ratio would indicate that they may have Alzheimer's pathology, when in fact they may not. Notably in this study, they did not find an association with no change in plasma p-tau. So it might be that p-tau is a better marker among these participants. I did want to touch a little bit on race ethnicity, because thinking about these biomarkers, there have been a lot of discussions about this. If we go back to kind of CSF as well as PET biomarkers, there are some studies that suggest that AD pathology may be lower among Black Americans as compared to white Americans. But other studies, we don't necessarily see that. And certainly a huge limitation of these studies is that those Black Americans that are enrolled are generally higher educated and much healthier, and not necessarily generalizable to the typical population. Now, the same thing with blood markers. Some studies we see a difference, and some studies we don't. One important aspect to think about, though, is that the comorbidities, so things I've just talked about in terms of obesity, chronic kidney disease, cardiac disease, the prevalence is much higher in African Americans and Hispanics as compared to white. And so as we're trying to think about some of these race or ethnic differences, we really need to move beyond just saying black-white differences, but to look at some of the reasons for this, because some reasons that some studies might see it and others not are the difference in the prevalence of some of these chronic conditions. So in summary, in terms of the comorbidities, as I showed, chronic kidney disease increases the Alzheimer's disease blood biomarkers, and certainly on an individual level, the lack of correct interpretation could lead to false diagnoses. The use of ratios may be more accurate, but much more work is needed to be done, especially at some of the more severe ranges of chronic kidney disease. Increasing BMI is associated with lower levels of these biomarkers. It's really unclear exactly how to think about this, and I'll talk about this a little bit more in the next slide, so I won't preempt that, in terms of whether it's a risk factor or physiological. But it may be, over time, especially if you're looking at these longitudinal aging studies, adjusting for BMI in a time-dependent manner may be important. And it may be important down the line, too, if more older adults are going on some of these GLP agonists, which can significantly reduce body weight as well. And then from what I've shown you to date, these are single conditions, CKD, BMI, cardiac conditions. It has been no work or no publications that have tried to look at the combination of these conditions and how that can really affect the levels. Particularly if CKD can increase the levels and BMI can decrease the levels, there's a lot of people that have obesity and have chronic kidney disease. So, how do you interpret the levels in those individuals? So, one thing I really want to talk about is that when we think about examining blood biomarkers in cognitive aging research and what I've shown you, yes, there are a lot of factors that may affect these blood markers more than I've showed you to date. But there's a big difference between physiological factors versus risk factors. So if we're thinking about, some factors may be risk factors, or that are risk factors, may affect the levels just because it's on the disease pathway. Others may be physiological factors and may not actually be related to, for example, Alzheimer's disease pathology, but may affect the levels for physiological reasons. So as an example, I mentioned with chronic kidney disease, when people adjust for studies, they don't see any difference between the levels and the biomarker levels and cognition. Well, I think a primary reason for this is that in the brain and kidney disease study, or the BRINC study, they really did not find an association between chronic kidney disease and Alzheimer's pathology or amyloid PET. And so to have a confounder, it has to be associated with your risk factor and your outcome. And if it's not associated with your outcome, that's not necessarily a confounder. So if you adjust for it, it's not going to do anything. But on a physiological scale, clearly it affects the levels. And so in this case, if it's a physiological reason, then it's better to analyze the data stratifying by that condition of interest. In contrast, BMI is something, we've talked about physiological changes, but we know that obesity is also related to a lot of brain function, as has been talked about today as well. So to be honest, I'm really not exactly sure how to consider BMI and obesity at this point, but I think depending on what our specific question is, we're going to have to think through how best to analyze these specific variables. So lastly, I just wanted to talk about some additional tests, thinking about interpretation of the blood-based biomarkers at the population level. So certainly, accuracy of the tests in real-world settings are not yet clear. I mentioned that most of the work has been done in specialized memory clinic compared to, say, amyloid PET or CSF. Haven't necessarily been looked at in light of a variety of chronic conditions as well as a variety of other factors. It's also, I think, important to consider that AD pathologies begin decades prior to the symptoms and increase with age. Therefore, there's a possibility, both clinical and research, that a positive test may be incidental. And this is particularly important in terms of thinking about cognitive aging. So we're really it's outstanding. We have these AD biomarkers, but as we've talked about in this group as well as yesterday, there's a whole lot of other mechanisms that impact cognitive aging in the brain and risk of AD as well as risk of other neurodegenerative pathologies. And so, even if we're looking at a cut point and this person may be positive, and they have cognitive impairment, that may not be the sole driving force of that cognitive impairment. There's likely a lot of other factors that are playing a role as well. So again, we need to think about this kind of in a whole and in context, and consider other mechanisms as we're doing cognitive aging research. And in closing, I would like to highlight U24 that we recently had funded. We call it the ADAC, Alzheimer's Diagnosis in Older Adults with Chronic Conditions. And the focus of this U24 is to build a national network that's focused on understanding how to utilize biomarkers for older adults who have cognitive impairment but also have multiple chronic conditions. And so as part of this network, we have executive committee, steering committee. We have 3 pilot projects that will be available each year, about $150,000 each. And we have an annual meeting. Our first one will be in Winston-Salem, April 29th and 30th. The focus of the initial meeting is to bring individuals in on the front lines, primary care as well as specialty care, to understand what they're thinking about these biomarkers, what they're facing in terms of patients' questions, and then what guidelines they may need in terms of going forward and what we can do to help them in that space. We also have a lot of working groups and look forward to anybody that are interested in being involved in that. Not just in understanding the accuracy of the biomarkers, but also thinking about ethical aspects and as I mentioned, guidelines. So sorry, I'm 25 seconds over, but thank you.
Okay, great. Thank you so much. That was great. So do we have, come on up to the mics if you have questions for the speakers. And I'm going to start out and actually ask Gina if you could comment on sleep and menopause.
Yeah, thank you so much for giving that. I realized that I had totally forgotten when I was talking about a menstrual cycle why that would relate to aging, and that is because in menopause, of course, our estrogen levels are much lower, and so that might really contribute to a poor quality of sleep as we get older. Also, it's possible, and there's no research on either one of these possibilities, but that menstrual cycling sets you up for more susceptibility to getting Alzheimer's later when you go through menopause. There needs to be some research on that.
Thank you. Go ahead.
Thank you for such an interesting set of talks. Actually, I had two questions. One is for Dr. O'Connell. You talked about using F1 crosses, and I just ask a little bit more why the decision to do that versus just using the BXD strains themselves, and is that what you'd recommend investigators more generally do, is to think about using panels like this and to address other kinds of questions?
So the decision to do an F1 cross had a couple of things. One, we could control the maternal environment. So the prenatal, like gestation, postnatal weaning, all of that's the same because the maternal strain, the dam strain, is the same. A lot of the genetic tool strains are built on the Black 6 background. So it also gives us a way to get in and actually manipulate for downstream validation, introduce disease transgenes, for example. So it kind of gives us a platform that we can build on and layer in additional things. It also brings in heterozygosity, which the actual original BXD panel doesn't have. Those strains are fully inbred. So making an F1 brings in heterozygosity, where you can have either a Black 6 or the DBA2J at about 50% of the alleles. It's not any more challenging to make than the original BXDs, and it has the same level of reproducibility. And within each strain, the individuals are isogenic. So the reproducibility, the extension of it isn't any more challenging than just using the BXDs.
Thank you. And then the other question that I had was, I'm sorry, I should let someone go.
Can we go over there?
Sure, thanks. Absolutely terrific session, really enjoyed it. Mitch Elkin from the American Heart Association. So I really enjoy hearing about all the discussion of sleep and cardiovascular risk factors and what they may mean for dementia and cognitive decline. Specific question for Kristine. Love to hear about the SMART trial. And I was wondering if you could just say something about how you envision that kind of personalized intervention being scaled within a research context to do a multi-center trial or for clinical care. How expensive would the intervention be? How would you go about doing that?
Yeah, it's top of my mind. So we've thought a lot about it. We tried to make the SMART trial fairly pragmatic in that we used EHR. That was why I wanted to partner with Kaiser, because they have this great EHR system. So we used the EHR to identify the risk factors, and then we validated them with phone assessments. We wanted to make sure they really had what we thought they had by doing some questionnaires and measures. So I think you could do that again, and that way the recruitment is fairly efficient in terms of identifying people at risk. You can exclude people with dementia, et cetera. Because of COVID, everything ended up going, actually phone, which was why I was sort of surprised we found something. The older adults, a lot of them weren't as comfortable with online. So a lot of this was all phone in the end. So COVID made this quite practical and pragmatic. We're now trying to decide next steps and whether we do more online. We'll hope to do a remote remote multi-site trial, and I think you can use EHR in a lot of ways. You can even use EHR for some outcomes or risk factor changes. So we're thinking a lot about it. I think there are a number of ways to go, which you allude to. Do you stay with primary care model? Do you try and do community participatory research? I think some of those I don't think I want to go sort of more with a Alzheimer's center group, because I think that's not really the group we really want to recruit. These are people at risk, not with cognitive changes. So anyway, but love to talk to you more about it. I think that where I think AHA, as you know, and the CDC, people are really trying to roll some of these things out in terms of public policy. So I think it's a really important time to be thinking about this.
Thanks.
Great. Right here.
Following on from that question from the AHA, I was going to ask something similar. So I'll move to a different part then, rather than the personalised. I wanted to hear your thoughts about some of the more local or even national policy level targets that some of these factors might have. So super interested in the personalised, but we've had the question on that. So where do you think the opportunities are at policy level, and who are the partners? I know you work with AARP substantially, but how do we change things at a local or national level in some of these factors?
Yeah, I was fortunate to be part of the CDC and the Alzheimer's Association have a partnership, and they just rolled out this roadmap, which I think is really exciting, trying to engage state-level public health offices to try and teach people about brain health. So I really think a lot of this is educational, that, a lot of doctors don't understand about brain health and, what dementia is or how you evaluate it. And so I think, to ask the public to understand some of this stuff is not really, it's challenging. So I think there's a really important role for public education about what brain health is, what are the risk factors, how is the heart connected to the brain, how is physical activity may be helpful, why maybe over the life courses might be helpful. I have a colleague in France who's done this beautiful video for elementary school. It's called My Brain Robbie, and so it's a really cute video, and it teaches elementary school kids about why they need to protect their brain, whether it's wearing a helmet or exercising. So I think this is a really exciting time, in this country and others to try and do public education.
Just on that, Brain Health Scotland has a similar programme for primary school children called STARS, and it's all about educating about exactly those risk factors: wearing a helmet, diet, social connection, hobbies. So I'll happily share those things as well, because they're absolutely beautiful, and they go right to that primary prevention level. So Thank you.
Right, to the middle.
Thank you. Thanks for the great set of talks. Liz Nielsen from the Division of Behavioral and Social Research at NIA. Sticking with Christine's talk, really just a comment just for awareness that I totally resonate with your need for the life course approach, but I wanted folks to be aware that we've invested in a number of educational cohorts, tens of thousands of individuals who are well phenotyped, particularly for their educational exposures, but in many cases all kinds of other life course exposures, blood biomarkers in a number of these cohorts, and groups that have, were born in the 40s through the 80s. So the Ad Health Study, the National Longitudinal Study of Youth from 72 and 79, Wisconsin Longitudinal Study, high school and beyond, and also some investments in Project Talent, which is actually over 300,000 individuals who were in school in the 60s. So these studies really represent an opportunity for collaboration in looking at these life course exposures, and I really think maybe somewhat underexploited because maybe not as much awareness in this area. And then a second comment and sort of a question to Dr. Koh really is touching on these questions about how do you tackle the structural exposures. And thinking about the design of these sorts of interventions, I always think about, what's going to be possible, even in tailoring to someone, if the sleep environment, for example, doesn't make it possible to address the sleep challenges for tranquil night's sleep. So I'm curious about, where you see your efforts going related to looking at these sort of more policy level things and where that might take you.
Yeah, thank you so much for that. I think policy is really important, and just actually since a press release of the early study that we did showing the helicopter police activity has already been reduced quite a bit. Maybe it helps that we have a new mayor as well, but the police were asking for, 10 more helicopters, and the city said no. And again, LA is the most police surveilled city. Why is that? There's no need for that. So I think policy differences and just becoming aware, city lights, street lights, windows, double pane air conditioning could help people prioritize their sleep in ways, and learning about the health consequences of poor sleep could help the city, the state, the nation, the world prioritize quality sleep. Thank you.
John?
John Disterhoft, Northwestern University. I have actually two questions for Dr. O'Connell. First, this issue of generalization of mouse data to humans. Would you comment on the implications of your findings for superager studies? I'm sure you've thought about this. And
yeah, that's a great question. And one of the advantages of mice, but something that even people who work on mice don't do, is age their mice long enough.
Right.
So even 22 months we have mice that will keep going. So it is still challenging to generalize to superager studies, but there's still a lot of, I think, parallelization that can be inferred between our very oldest mice, as long as we age them out long enough, and it'll be the females that make it that far. The male strains often don't. But yeah, the comparisons with the superager studies, particularly for life course, that's incredibly important to understand what earlier life impact is on that very, very late life. But I think even people who work on mouse models, we need to be cognizant of how old we age them.
But also the importance of genes, right? The genetics.
The genetics are what the lifespan is determined by genetics. Right. It's not every strain that makes it that far, right? It's a select subset of strains that live that long. And longevity is dependent on background genetics. So if you're only studying a single strain of mice, you can't study interactions if you don't have anything to interact with.
And the other question is, in your the two pictures you showed, or slides you showed of fat measurements, it looked to me like the hippocampus in the high-fat diet was considerably smaller. Was that accidental, or is that what you find? I realize those are not histological sections.
They're not histological, and I think it will be important to go back and do that with more accurate histology. There is a difference in abundance in lipid in the hippocampus. It's not hard to imagine that is influencing hippocampal volume.
Right.
And the part that we really see the biggest difference is actually in the dentate. The lipid composition of the dentate gyrus is really quite different. between those two. It's also quite different in CA1. But CA3 and the rest is not as different. It will be, yeah, we noticed that too. Okay. So whether it's real or it looks, because there is no, it's crazy, but there's no structural information in that image. That was all just lipid, which is structured.
Yeah.
But,
thanks.
Yeah, thank you.
Joel Salinas with the American Academy of Neurology's Brain Health Initiative. Definitely on the same page regarding the life course approach. This question is for Dr. And thinking about the next iteration of SMART, what consideration have you given to other kind of domains to be addressed, like income volatility, which there's some great findings in cardia related to income volatility in midlife, but also things like socialization, loneliness, social support?
Yeah, so, people always say, well, what's the one thing I should do? And of course, what I usually say, tongue in cheek, as well, improve public education in this country. I'd say the same thing about income, inequalities, but, there's only so, I wish I could fix that. So your point is extremely well taken, which is why I think, expanding this to not Kaiser, for example, might be very important to because I think there are a lot of risk factors that vary by income, of course, and by region and race and ethnicity. So, or immigration status. So I think it's a really open question and a really rich opportunity for us to try and do better in this country in terms of public health in general, but some of these things in terms of brain health. But it's hard to say. Let's reduce income inequality and improve education. But I think your point is well taken. Social isolation obviously is getting a lot of attention now. I think it's very important. That was one of our risk factors we looked at, was social, and actually we were able to improve that. It was tough because it was COVID, and we actually have a paper where we showed that COVID, tanked all the risk factors, of course, but tanked them less in the intervention group than the control group. So yeah, social isolation's gotten a lot of press, obviously, because of some of the emerging research and the Surgeon General. I think it's really interesting, and it goes with other things too. So I think that intersectionality of social isolation with some of these other things is really important to look at.
Thanks a lot for a great session to all the speakers. Michelle, I have a quick comment and a question for you. Really, really, important work. And as a clinician, I'm increasingly worried about the rollout of these blood biomarkers in situations where people might use it for screening. People might be accessing them or wanting to access them because they're simply worried about their memories in the absence of, a clear clinical workup and a diagnosis of cognitive impairment. That's something I worry about, especially because I have patients in my clinic, at least one of whom has gotten one of these tests. And it's worrying that this particular test is based upon, quote unquote norms from a conference abstract based on about 20 patients. And so the fact that these might eventually come out in direct to consumer settings is worrying to me. I'd like you to comment on that if you can. And then the question I have is with regards to acute sleep deprivation. So we know from this PNAS paper in 2018 from Nora Volkov and colleagues that even one night's disruption in sleep can increase brain amyloid PET signals. So in that context, again, when we're measuring these blood biomarkers, either in clinical practice or in research settings, how important is it to ascertain that, have you had a good night's sleep, or have you been sleeping well over the last week before we actually go on to interpret what these biomarkers are telling us?
So, I mean, great comments, and I'm completely in agreement with you. You've got some people that are coming in that see the headlines, hey, we've got this blood marker, can tell me if I have Alzheimer's disease, and not understanding the difference between pathology versus symptoms and whatnot. So I understand there's a lot of people that are coming in and wanting these tests. I think, as you said, these tests, number one, should not be used for screening purposes, even including those that may have a family history. Secondly, they really should be used in combination with a workup. So it shouldn't even just be a MOCA and then the blood test. You need to look at other potential reasons for the cognitive impairment and what might be driving that before the test. Fortunately, the direct-to-consumer test has been taken off the market. So thank goodness for that, because I think that caused a lot of problems. The other thing that is very important that we aren't talking about enough are the ethical and policy implications. Because as these for clinical purposes, right now, I mean, we are starting a couple of primary care real-world cohort studies, but we can call them research, even though very pragmatic, so we can keep the information out of the medical records. But once they are in the medical records, they can affect long-term care insurance and disability and life insurance. And so, again, we need to consider that, and that means that physicians will need to take more time to discuss that with patients prior to having the tests as well. Sorry, you got me on my soapbox a little bit. I think there's, I think they can be used appropriately, but in limited. And you're right. So in terms of sleep, I haven't seen as many studies that have looked at sleep and the blood markers, similar to what you said with CSF and PET. I know there are a couple studies that have looked at, okay, you're doing it, it's coming out soon. But there are a couple studies that have looked at diet and fasting status, and so they have seen some effects there. Again, not exactly sure how to then take that to the clinic for interpretation.
Can I just follow up on your point? It's such an interesting area, now, and we're ahead of ourselves. But can you say more about why you don't think it should be used for screening? Because a lot of people think it might be used for screening in the sense that you have somebody who has cognitive complaints, you do a MOCA or whatever, and some people think, well, maybe you do that, and then if it's positive, you send them off to the specialist. If it's not, you are reassured. Can you say more?
Yeah, actually, thanks for that question. So when I was thinking about screening, I was thinking, there's this discussion that these blood markers are the next cholesterol test. And so with cholesterol, let's screen these, every so many years as far as prevention. So I was thinking about it more in terms of that among asymptomatic individuals. And there's a survey that has gone out, I think we'll be presenting it at AAIC, but of primary care physicians, and a third of those surveyed stated that they would use the blood markers for asymptomatic individuals if they had a family history of Alzheimer's disease and were worried about it. So in those cases, that's not appropriate, because we don't know to date, really what the prognostic value of these markers are. But in terms of what you said, so yes, somebody has cognitive impairment, and then you're trying to understand it, I think that's okay.
Okay.
Awesome. Hi. Thank you so much for some phenomenal talks. I've been blown away the last couple days. So I'm Larissa Strath. I'm from the University of Florida, and I have two quick questions for Dr. O'Connell. I'm also a nutritional neuroscientist, so I get really excited when I see, because there's not very many of us. So what I'm curious is, one, was the makeup of your diet? So you had a high-fat, high-sugar diet. Where were those nutrients derived from? Were they plant-based, animal-based, refined, not refined? All those kinds of things.
They are plant-based, refined. It's actually a commercially available diet from Research Diets.
Okay. Yeah. Okay.
Yep.
Yeah.
It's sugar and it's a plant. The fat is plant-based.
Okay, sounds good. And then my second question is, given the genetic component and also the growing evidence that the diet and nutrients can interact with the epigenome, are there plans to look at that in these mice? And then do you think, knowing your project the best out of all of us here, that you would actually see some of this passed on to the offspring of these animals?
I would love to do what you're describing. Actually, the design of the BXD panel, the design of the F1 BXD panel would work the best if the fathers were, because that's where the genetic diversity comes from. If we switched it and put the mothers on diet, that's a really interesting question in and of itself. It actually brings in genetic diversity on X, which we don't have. It's a really important question. We don't have plans to do it in the immediate term, largely because it's such a big study, and logistically it's tough. But it should be done, and it's a very tractable question in mice. It's very easy to manipulate them. It's very easy to follow them and intervene and control their environment. So someone should definitely do it. And I would love to help and advise on how to design and execute that study.
Sounds like you and I need to chat more later.
Thank you. Rin?
I just want to pick up on the discussion about the plasma biomarkers, because I think this is some of the most important work to do, because it's the tip of the spear, so to speak. There's now something that for large groups of individuals looks like it has a lot of signal value. And so to do this next level of work where you see the heterogeneity and that it doesn't have signal value under these conditions, how do you make sense of that? My guess is a lot of the other things that we think are more promising actually have all these issues as well. We just don't know it yet. So given that, with a plasma biomarker like this, I guess at this point I'm not willing to accept the answer you can't get an inexpensive, accessible plasma biomarker to be screened like cholesterol, because I think a lot of these treatments we want to get in early, not when people are having the symptoms. So I guess, having thought about all the challenges, can you imagine a world to make this a high signal at the masses? Because it's one of the least expensive, most accessible opportunity spaces. So I'm just kind of curious.
Actually, before you answer that, can I add to that question, which is, I know race is a social construct, but still, we really need to consider something, because the genetic relationship, Casey Dieters and colleagues found the genetic relationship between ApoE and Alzheimer's disease is not present in the Black population. So it might be that we really need to, what's that?
Well, depending on African ancestry.
Maybe opposite, African. Maybe.
So quick, and then come back to that. So that is one thing to watch out for, because there are some clinical tests that are developed based on algorithms, and so they take into account ApoE genotype in their score. So would not suggest necessarily using those. We don't know how that works in more heterogeneous populations. I think based on your question, yes, down the road, ideal situations, it'd be great to have these as markers and think about them as a cholesterol test. I think there's, certainly some things that need to be done before then. So we do need to understand how they work in heterogeneous populations. I was talking with Jose Luxinger before this, and in the Look Ahead study, where they're all type 2 diabetics and obese, we are not seeing any associations between these markers and cognitive decline. And in fact, with p-tau, we're seeing it in the opposite direction. So we just got those data last week, so we need to try and figure out what's going on. But we need more work there, certainly more racially diverse, look at some of these other factors. I think another question, too, though, is the prognostic value. And, right now, some individuals, die with their heads full of plaques and tangles, but don't necessarily have symptoms. So how can we put that in light and really understand what that is? A third thing I think we need is education, really on the part of the lay public and healthcare providers and whatnot, because there's this idea that Alzheimer's pathology is the same as Alzheimer's disease dementia, and we need to kind of change that discussion, where particularly in asymptomatic individuals, it's a risk factor, it's not a diagnosis of Alzheimer's disease. And then sorry, I had one more thing, and now I forgot. But yes, I do think it's, and then the last thing again comes back to ethics. So until we have these policies in place that protect patients, I'm very concerned about incorporating these in asymptomatic individuals. Because if we roll these blood markers out and we end up harming a lot of people, there's a lot of distrust of science now, but there's going to be distrust of these blood markers, and then we're really going to have a lot of problems.
Hi, thank you for these wonderful talks. I'm Carrie Sheets from the University of Minnesota. I had a question for Dr. Yaffe. You showed that cognition improved in both the control and intervention group and mentioned that that's common in these primary prevention trials. I was wondering if you could comment on some of the hypothesized mechanisms between them.
Yeah, most people think it's somehow a practice effect. It makes sense. Another possibility, I guess, is that because of the educational material, maybe it was a bit of an active control. I don't know. We did see the difference in terms of risk factor change, but it may be that most of the control group actually was worse, but again, some of that could have been COVID, and it's a little hard to disentangle. But most time people think it's practice effect. But I have a lot of neuropsychology friends here. They could weigh in. I think that's probably because I think we saw that in certainly in Finger and in a lot of the multi-domain trials and Sprint, et cetera. A lot of times people do get better. Here in the middle.
Hi, Chandra Reynolds from University of Colorado Boulder. My question is directed towards the biomarker presentation, and interested in trying to get a picture on the dynamics of these biomarkers and our understanding or lack of understanding prior to midlife. And it seems to me with the discussion about the ethics of the rollout, I think there's a real dearth of information earlier in terms of how these biomarkers might change and, what recommendations you might make in terms of trying to prioritize that in research.
Yeah, so I think that's a good question. We have looked at the changes in these biomarkers from age 30 and on. Something like NFL absolutely increases with age from the time you're a baby. And so clinically, NFL will have age-specific cut points. How that relates to further disease process and cognitive aging, though, I don't think is fully understood. We had found that plasma p-tau, it looked like it increased with age, starting around the age of 65 or 70. But then when we stratified by amyloid status, it really only increased in those individuals that were amyloid positive. Now, again, that was a primarily white cohort, and we know that ADRD processes start earlier in some underrepresented minorities and other cohorts as well. So there's absolutely a need in more of these diverse cohorts to understand how these markers change over time. And then, with the comorbidities too, that they'll be earlier as well, so we need to think about that. There has been, I talked with Jet Dage quite a bit about this because he had wanted to go down earlier. His thought was that with p-tau, it may be elevated early in life and then drops down and then increases again. But we haven't actually gotten the samples to be able to look at that really across the lifespan.
Can you comment about how much of the data is really coming from single shot versus longitudinal work, though? Because that's where I think there's a real gap.
Yeah, no, I completely agree with you. The vast majority is still single. And so when you look longitudinally at the baseline, and then how does that change? And there's still not enough focus on the individual variability across time.
Okay, we only have time for one more question, but one more. And then hopefully everybody can ask at the break.
Thanks. My name's John Brady. I'm with McKnight Brain Research Foundation, but my day job is that of a family physician. And so I appreciate all of your lectures today, and I've got so many questions for all of you. But given that you went first, Dr. Poe, I was really interested in your the description of slow-wave sleep and how it's healing. My question is, given that we also know meditation induces slow waves in the brain, can you substitute meditation during the day for a little bit of sleep at night? And has that been shown to be reparative as well?
The simple answer is that we don't know, because we've never measured acetylcholine and we've never had a rat meditate. But if there are real slow waves, it's quite possible that acetylcholine levels are low, and it might be that that's enough. But we'd have to measure acetylcholine levels in humans meditating or teach rats to meditate, which actually isn't as crazy as you might think. You can actually have them do breathing exercises. You can teach them to do breathing exercises. So it might be that we can at least get them to do, meditation in that sense.
Thank you.
All right. I just want to say thank you to all of the speakers with great talks, and that will close our session. Thanks.
Thank you. We have a brief break this morning, so please be back at, I think it's 10:30. Correct.
Thank you, and welcome back to our final session. I suspect some people will be wandering in as I kick this off. I also just wanted, as the last session of this two-day symposium, I just also wanted to thank Molly, John, and also Dave for organizing this, and the McKnight Brain Research Foundation for bringing together such an extraordinary set of speakers and the opportunity. And I think we've been seeing in this sort of push since last time we've convened is all these extraordinary technologies that are even allowing us to see, as we saw in the last session, some of the challenges. This last session is about the ultimate goal of some of these things. How can we turn them into policy recommendations, therapeutics? How can we test the knowledge that we've gained to impact the aging brain and cognition of individuals in the real world? And we haven't done enough. There's been challenges, there's been starts, and a lot of things haven't generalized that look promising in academic settings. And so this session fundamentally about is how do we do better? What are innovations using computational technologies, new strategies to guide studies to be more efficient, trials to be more efficient, and what can we learn from the existing trials that are ongoing or have been recently completing that have had some successes but also some challenges? How can we learn to do better? And so in this session, I'll be chairing. I'm Randy Buckner, and also Dr. Michael Yasov from the University of California, Irvine. And we're going to kick it off with Anne Draelos, who is going to come to us from the University of Michigan and be speaking on machine learning for adaptive experimental designs. Thank you.
Thank you. And I just want to say thank you to the organizers for inviting me. I'm really delighted to have been here for the past couple of days and learn a whole lot more about the study of neuroscience for aging contexts. So I've been an assistant professor for a little over a year. My work has primarily been applied to vision, motor, a variety of contexts as I work with sort of generalizable computational tools. And I just recently got into the field of aging in the past sort of 6 months or so when I met Catherine Kazarowski when she moved to Michigan. And so I'm really excited to tell you about different ways where sort of some of my work could be applicable to the study of cognitive aging. So my lab just developed new machine learning methods to address the problem of designing causal or interventional experiments that can scale to high-dimensional spaces. So by high-dimensional spaces here, I mean the increasingly rich and complex data that we are acquiring in neuroscience. So I've put sort of 3 categories of examples on the slide here. So tens of thousands to millions of neurons we can record from simultaneously in the brains of living animals. Finer spatiotemporal measures of externally observable behaviors, and then pushing towards more naturalistic and changing environments or stimuli to present to an animal. Right? And so not to mention genetic components, other physiological features, and you see that we have this really true wealth of data. And when we add a time variable to all of this to study things like aging, again, you've increased the dimensionality of your data. So we would like to be able to make provable claims about, for instance, how these thousands of neurons are acting together in response to complex external stimuli to evoke fine-grained behavior that might vary as a function of age or individual. But the time that we have to conduct experiments that are directly and ideally causally testing hypotheses has remained the same. We only have 24 hours in a day. Right? We can't measure neural or physiological responses to all possible situations of naturalistic environments or test all possible ways to intervene during behavior throughout the lifespan of an animal. So how do we choose? So the idea is that we have scaling experiments into these high-dimensional spaces is to use adaptive experimental designs. Now, if you've played one or more of these games shown on the screen, you have probably employed an adaptive strategy to do so. So I'll just give you a simple example here with a game of 20 questions. So I think of something, probably an object, and it's your job to ask me yes or no questions to figure out what that object is. Right? So for example, if I were thinking of a duck, you could solve this by asking a series of questions like, is it alive? Is it bigger than a horse? Is it a mammal? And so on. So each time you receive an answer to the question, which allows you to intelligently pick the next best question to ask. But what if I asked you to pose all of your questions in advance, write them down and hand them to me? You could probably figure out if I were thinking of a duck, but only if you generally knew a smaller subset of category of what I was thinking of ahead of time. Right? So the reason that this is very winnable for you is because you're able to leverage information, leverage data as it's being acquired, which allows you to guide selection of the next best question to ask. Right, and so what I'm hoping to show you today are a number of possibilities for integrating machine learning models into adaptive experimental designs, and how iterative and adaptive methods in particular can be applied to many different labs in the study of neuroscience and aging. Okay, so first I want to talk about iterative models. So one key aspect for the sort of power behind some of the models that I'm talking about is their ability to work with diverse data sets. Indeed, some modeling frameworks need that diversity in order to generate robust predictions. So including data across a population is essential. And it's the same method of interacting with diverse data that allows us to design models that can be tuned to specific individuals, basically personalize them. And I'll be talking about some probabilistic methods that let us do this. Secondly, these kinds of methods allow us to immediately learn from intervention results. This is like that game of 20 questions. So employing a kind of iterative and adaptive strategy can allow us to be exponentially more efficient at ascertaining something of interest, as well as allowing us to determine some sort of optimal allocation of tests when you have a limited number of them. And in this case, I'll be talking about some Bayesian optimization. Okay, so one kind of variation that we might want to think about including is in models of neural dynamics. So first, we want to discover new patterns of neural activity as a function of time. So identify latent features in our data as we are continuing to acquire our data. So frequently, we might see repeated patterns of activation across time or trials. If you can see on the slide, beneath the orange circles, there's sort of curved gray trajectories, right? And there's some repeated underlying pattern that your brain can all recognize, but there's still some variation there. You can think of these as living in a low-dimensional space, similar to a PCA space. Rather than seeing each of these curves as a new pattern or feature, we instead want to characterize them as some single feature with variation around a mean. So we developed a model visualized here in orange that uses a hybrid Gaussian mixture and hidden Markov model to automatically learn these kinds of features and capture that expected variation. So with this probabilistic approach, we also naturally stay flexible to the identification of new patterns as time goes on. And so here are some videos of dynamics that the same algorithm is able to learn, to quickly learn how to model, tune for a given individual. You can see here we're looking at data sets. The top is from a macaque and the bottom one is from a mouse. And this is the same algorithm applied to each of these data sets. So data-driven modeling can help us identify new latent features of interest. And we've already seen some really great examples throughout the symposium, throughout the summit, of finding new latent features. But what you can also do is to use unsupervised machine learning during the data acquisition process and learn correlative features across data types and identify which quantities of interest we should be paying the most attention to and nominate for future study. So here I'm using data from the publication cited on the top right from Ann Tropson's lab that looked at identifying which behavioral features from this video of a mouse are predictive of ongoing neural activity. So rather than predefining parameters of interest like pupil diameter or lick rate, they found new latent features, for instance, that are widely distributed across the cheek, highlighted here in orange-red, that are significantly correlated with neural activity on a single trial basis. So what we developed was a new form of streaming dimension reduction that could learn latent features of interest as the data are acquired. So not looking at it all at once. And here we're using a streaming form of ridge regression that showed very similar results in only a minute or two of data. So if you look at the bottom right figure, you'll see basically convergence of this model in about 60 seconds. So with we're able to identify the same kinds of relevant features that might have otherwise required sort of taking many, many hours of data and then doing a post hoc analysis. So starting from scratch, we can look at these ongoing data sets, put new information into the model, and say, here are the latent features that are relevant. You should measure these. You should intervene on these. And this might be different for each individual, but if it only takes a few minutes of data to learn these features, then tuning it to the individual is very possible. So I want to talk about how we can use these kinds of models that update themselves in response to new data to help guide our choice of what and where to measure. So basically, what kind of new data is best to collect. And this is work I did with Eva Naumann's lab at Duke University. And so her lab studies the optomotor response in larval zebrafish. So we wanted to address the question of, how do we choose what to measure? How do we know what's relevant to our neural population? If you look at the far left, this is an example of a single neuron tuning curve in response to different directions of motion from moving gratings. So you can see it's just a map of neural firing rates as a function of direction measured at 45-degree resolution, so 8 different directions of motion. If we had lots of time, we could choose to measure this at finer resolution. So we're going to do this at 15-degree resolution. And what you find is that a neuron who might have been identified as selective to backward right motion is in fact bimodally peaked. It's both selective to backward right and backward left. Okay, so this gives us a richer picture of what the neurons are responsive to, which we think will be able to scale up into a richer picture of what the neural circuits are actually having those sort of underlying factors. But the instant we try to take this into higher dimensional space, even 2 dimensions, presents us with a problem. Now we have 600 possible stimuli to present to this fish. If you want to do 3 dimensions, now you're talking about thousands or tens of thousands of things that you might need to measure. All right, so this is clearly infeasible. So what we're going to do instead is use an online Bayesian optimization approach. So here, bottom left, we're going to be using 2-photon calcium fluorescence imaging to give us this neural activity. We will start by showing a particular stimulus and observing the neural response. We incorporate this into a model using Gaussian processes of the neural tuning curve in 2 dimensions, which is that heat map there. Importantly, we don't just get an estimate of the neural response, but an estimate of the uncertainty that our model has about its predictions. And this is what we can use to guide our choice of where to measure next. What new data could maximally decrease our uncertainty while also still learning the stimulus sets that evoke maximum neural responses. And so as we basically choose the next selection, we observe a new data point and we iterate until we have a particular confidence level that the model has reached. So this is just a quick video of this happening. You can see neural responses, the tuning curve estimate getting refined in the center, and our uncertainty on the far right going to black, which is going down. So as we sample, the uncertainty goes down. And importantly, this is what allows us to know when we can stop measuring and go on to target the next neuron. With robust estimators of uncertainty in many kinds of these models, we can leverage early stopping and become much more efficient with our data collection strategies. So when applying the strategy to a population of 300 neurons, what might normally take hours of data collection instead takes maybe 3 to 5 minutes. And again, these methods can adapt themselves to a particular individual, or in this case, brain area, automatically. So here we see, this is a population heat map of the peak neuron tuning in the pretectum and optic tectum regions. So the white X's denote where the algorithm chose to sample. So you can see it's choosing to measure different locations between the pretectum and the optic tectum, depending on the regions where more neurons are indeed most responsive. And it can do this without any human intervention. So this experiment can basically rapidly identify where it should be measuring, basically autonomously. All right, so one last example to showcase how these kinds of adaptive designs can be applied to the choice of targeted or direct interventions. So here we're considering the problem of network inference, where we want to learn which neurons or nodes in a network are connected to which other neurons. This will allow us to get at circuit connectivity patterns, But we don't want to just learn this on average. We want to learn this for an individual. So we need to be able to learn this really efficiently so that we can identify this in one particular model organism. Again, here we're looking at the larval zebrafish. We can use techniques like photostimulation to perturb a neuron and measure the responses of all of the other neurons in the network. So a sort of typical, straightforward framework for doing this: perturb a neuron, so intervene once, measure the responses, and then intervene again, and do this for each of the neurons in your network. So for a network of 100 neurons, this would take you about 40 minutes. For a network of 1,000 neurons, this will take you maybe 7 hours. By the time you scale up to 10,000 neurons, which is really only 10% of the network in a larval zebrafish, this will take you 3 straight days of constant intervention. Right? So we do not have this time, and we do not have this number of interventions. So what we did instead was turn to the statistical framework of group testing. So here, we're not selecting one intervention at a time. We do a group of them simultaneously. We observe the network responses, and we can infer very rapidly the full connectivity structure of the network. So not only is this faster because we're using multiple interventions, but again, we can rewrite this problem using variational Bayesian inference. That's the formula at the bottom. And what this does is it allows us to obtain a measure of uncertainty in our network estimates. So now we don't just need to choose random interventions. We can instead do an intervention, observe the responses, incorporate this result into our model, and see where is our model most uncertain, and choose those areas for the next intervention. So this kind of adaptive procedure scales really well to large networks, if you look at the diagram on the right, which enables us to fully map a network of 100 million, or 10 to the 8 parameters in less than 2 hours. This is in simulation. The experimental results are in progress. So I hope I've shown you a few ways in which incorporating machine learning models into an experimental setup and not just using them post hoc could be extremely useful for enabling new kinds of efficient, powerful experimental designs. These methods can be used across diverse population and to tune models to specific individuals under consideration. They also allow us to incorporate data as it is acquired, and thus we can rapidly learn from intervention results in potentially exponentially more efficient ways, which is very desirable in the case where we only have a limited number of trials during which to intervene. I should also point out that none of these algorithms were particularly specific to a model organism. We applied them generally across mice, fish, macaque. I'm working on octopus as well now. So the data type, the model organism, weren't particularly important beyond there being correlative time series. And if you'd like to discuss how you can incorporate more of these machine learning models into your experimental designs, I'd be very happy to chat with you about it. With that, I'd like to thank my lab. Thanks also to my postdoc advisor, John Pearson, and my collaborator, Eva Naumann, and my funding sources. Thank you.
Thank you for that spectacular talk. We will continue with Dr. Nathan Price from the Thorne HealthCare, who will be speaking about another innovative approach taking digital twin models of cognitive health and aging.
Thank you. Great to be here. It's been really interesting to hear so many fantastic talks. A lot of ideas off the last one, too, that I'm excited about. So I'm going to talk a little bit today about digital twin models of cognitive health and aging, and at the end, especially about how this leads us to a different way of thinking about how we might design clinical trials. So I'll start very broadly, just in terms of kind of my background and what my perspective is. So I'm very interested in kind of as broadly across our medical and research enterprise on the idea that we intervene much too late in general, and we spend way too much time studying only late-stage disease and not like the earliest transition states to it. I wrote a book on this with Lee Hood for Harvard Press last year called The Age of Scientific Wellness. And we've been doing these large longitudinal studies in healthy people now for about a decade, which I'm not going to get into a lot today, but it really influences the way that I think about this, especially as we're thinking about in this session cognitive aging and what can we do. We saw some beautiful data and examples in the last session, which was really a fascinating session, about how often things that happen early in life really manifest and make a difference later. So just to give a sense of my perspective, one quote that I really love about this actually came, I was going up to give a lecture at RPI, driving in the car, heading up. I was listening to I like to keep up on the latest literature. I'm slightly behind. This book was written 2,000 years ago by Seneca, and he was talking about longevity. And he had a quote that I really liked, which was, he said, as he was explaining to his young protege, for it makes a great deal of difference whether a man is lengthening his life or his death. And I thought that was such a beautiful way to put it. For those of us that are, maybe a little bit in the longevity or healthy aging space, his next piece of advice I found totally fascinating, because he said the latest craze back then that he was getting into was periodic fasting. And we've advanced now to intermittent fasting, so we've come a long way. Okay. There we go. So obviously in cognitive aging, this makes a huge difference. I wrote a piece for the LA Times on this, again with Lee, last year. But one of the things that really strikes you when you look at, say, Alzheimer's and what you can do about it is that when you look at drugs, they're highly expensive. We've spent, depending on your estimate, $300 billion up to some estimates are nearly $1 trillion cumulatively now on anti-amyloid therapies and other drugs over the decades, with very limited benefit. However, if you look at prevention, like the finger trial, the ongoing pointer study, things of this nature, the benefits are actually measured in years of delay, and the effect sizes are much larger. This matters in particular communities as well. One of the really striking findings, the Hispanic community in particular is highly responsive to this. The estimate is that 56% of Alzheimer's is avoidable or could be eliminated through lifestyle intervention. That's data that are coming out of these studies. So we know that prevention or coming in early, focusing on cognitive aging, makes a huge, huge difference. And so there's a lot you can do over these trajectories. This has become a lot less controversial over the last few years. There was a great study in The Lancet that just was published on modifiable risk for Alzheimer's disease, the kind of things that there's a consensus around that you can do in order to maintain your brain health for longer. And you can see the list of things that are there. Many of them have been addressed in the meeting that we've had here over the past couple of days. So coming now to digital twins, one of the things that we've done over the last 3 years, and this was a collaboration with a startup company called Embody Bio and a colleague of mine, Tom Patterson, for many years, but basically was to build a quantitative physiologic model of how does the brain maintain health. So this started out as a model of looking at ordinary differential equation model where you could build out mechanisms. There's then a Bayesian network overlay on top of it to deal with uncertainty. And so you're able to then simulate trajectories of cognitive health over lifespan. Now, I'm not going to get into it in the interest of time. This has given me a very different view, I have to say, into what I think are the main drivers of Alzheimer's disease. But one of the things that this really gets at is how does the brain maintain enough energy to stay alive, right? That's one of the big things. 20% of your body's energy use. It's 2% of biomass. It's a huge energy hog. The oxygenation in your brain goes down as you get older. Solving those equations for maintaining energy becomes harder and harder. It turns out that you want to keep cholesterol levels in astrocytes, these supporting cells around neurons, low to keep energy efficiency high under low oxygen conditions. ApoE4, or ApoE, right? The gene has a role in transport of cholesterol out of those cells. ApoE4 does it very slowly. Therefore, energy generation gets in neurons is less efficient. It's poor. Therefore, they die. ApoE2 does it quickly. Therefore, that energy efficiency stays high. You can model all these over time. So we'll get into a lot of those, or actually we won't get into a lot of that detail, but if you want to chat about it later, happy to do that. Now, as I mentioned, this model starts then as a model of brain health, right? Maintaining energy, taking out the trash, right? What you do a lot when you're asleep, which we heard about earlier, microglia functions, all of those kind of things into the model. Now, once we built this model to try to say how do you maintain health, then of course you can layer onto that different aspects of the drivers of disease, right? So this is just kind of a sanity check. So we did this for Alzheimer's after the fact, and so here. These are known effects of genetic and lifestyle risk factors. I see that in my template I forgot to delete the confidential down there. This is, of course, not confidential information. This is like generally knowledge to anyone in this room. But known effects of genetics and lifestyle risk factors on development of Alzheimer's disease, right? We know ApoE, whether you have ApoE4 giving you high risk, ApoE2 low risk, and so forth. And then on the bottom there, I've just listed from various papers some of the known risk factors. So if you're looking there near the bottom, so glomerular filtration rate. So if your estimated glomerular filtration rate is high, your Alzheimer's conversion is low. If vitamin D is low, Alzheimer's also low. If your cortisol, your stress levels are high, and so forth. So this is just a compilation of data from lots of studies and lots of papers on what we know about the conversion rates and the hazard ratios to Alzheimer's. So one of the things that I briefly described was to generate digital twins on that. And we've now generated about 26 million of these on top of this core model. And so one of the questions was, how similar is this population then that you simulate based on these data? And there's data and insights behind the model from about 1,200 papers, and we've compared it now to about 30 different published clinical research studies and human research trials. And this is what it looks like, is that when you evaluate that population, so the solid lines here are the digital population, the fatter lines are the actual data, what you find is that population looks an awful lot like the actual population. So some of the things I mentioned before on the effects of ApoE4 dynamics or ApoE2 dynamics on being able to explain like when people fall into dementia. Turns out if all you take is the two facts of the lowering of energy efficiency based on those effects of ApoE4 or ApoE2, that in fact gives you back these Kaplan-Meier curves. So you can center all of this around basically needing to keep neurons alive from an energetic level. So we get into all of these kind of things as we're going through this so that we can do simulations then, again over time, that relate molecular level detail to what's happening in patients. So this then leads to a digital twin simulation. I'll just show a version of this here. See how well you can see that. But basically, we can take measurements of a lot of those modifiable risk factors that we determined. So the case that's on this particular slide, this is a man. He's 50 years old, has 2 copies of the ApoE4 gene. You can see some of the things there. He has really low vitamin D, sleeping terribly. So homocysteine is elevated. Phosphatidylcholine intake dietary is good. Methionine is good. Cortisol levels elevated, but not terribly bad. A little bit low on glomerular filtration rate and so forth. So you can put this kind of information in, again, quite readily available to measure. And what you get out from a model like this is you get a probability distribution. So here shown on the right here, where you see that histogram, is a probability distribution. So we would say, given this person's data, that the most likely age of onset for dementia for this individual would be 61, and we believe there's a 99% chance that this person doesn't get to age 69 without having a diagnosis of Alzheimer's disease. So that is now you should think about this a little bit like the Ghost of Christmas Future. This is sort of, if these shadows remain unchanged, you're not doing an intervention. What is the expectation given where you're at? Now on the bottom, what we have are a series of potential interventions. In this iteration, these are focused on things that are very safe to do in a otherwise healthy individual. Exercise, improving their sleep, dietary supplements, nutrition, things of this nature. But what you can see then, going there from the bottom, is that you can calculate the percentile responder that you would expect this person to be to each of these, and the expected benefit. Now, for the purposes of the talk today, the thing I want to most focus on is if you're looking at the bottom there, you're looking at things like B complex, phosphatidylcholine, increase exercise to get brain oxygenation up, phosphatidylserine, and so forth. For most of those things, Most of those interventions, if you do them one at a time, what you'll see there on the bottom is that the prediction of the change is 0. There is no predicted change in many, many of these cases for any single intervention. But if you go to that top line where it says all, now all is just to make the slide shorter. We actually compute every personalized combination, and you can optimize the one that you want, and we have a ton of data on that. I won't go through today in the interest of time. But there exists a combination for this person, though, that we believe that there are 6 extra healthy brain years of life on the table on average for this individual where you can shift that. You can tell them precisely what that is, and you can give them an estimate of how much benefit you would expect them to get. Now, just to give you a sense for how this changes person to person, I'll just run through a video here, or an animation, just so you can see this. Hopefully this is going to run. Yes. Okay. So this you can see. I don't think without a computer I can pause this. But anyway, you can see how much this is jumping around, or how different an individual's pattern looks like. And you'll see some people have quite narrow ranges. There's only a little bit on the table. Some people have very big ranges. Now, one of the things, and this relates also back to Anne's talk, is, especially when you see some of these really broad ranges, you can use these kind of models to say, well, what's the next thing I'd really like to measure to try to get a more focused prediction on this individual, and how far can I push this into the future? You can also do this for drugs. We've done this as a proactive or a prospective simulation, for example, of TREM2 agonists. TREM2 agonists we predict would have about a 6-month benefit for people after diagnosis, but you get a curve where there's this long tail, and there are people, or at least there's digital twins that we would look at that would get 3, 4, 5 years of benefit. When you then run them through this type of simulation, you can then pull back, well, what are the special characteristics of those people? What makes them a super responder? You could imagine using such an approach to generate, maybe half a dozen or a dozen different therapeutic strategies, hoping that, you can find combinations to which people are super responders. Okay, so the main thing I want to talk about to finish here is around how the notion of digital twins can help us with personalized evidence-based medicine, so different styles of clinical trial design. So I want to give an example. So one example is from observational studies, elderly people who are low on vitamin D get Alzheimer's at quadruple the rate of those who don't, right? Observational study has all the biases and problems that we know of. But when I gave the example of the Lancet study, for example, we do not include vitamin D as part of a recommendation for the prevention of Alzheimer's, right? So you'd say, well, the observational study, why would we not do that? And of course, the answer is that we've done a few randomized clinical trials, and vitamin D has failed on those. So it has failed on those clinical trials. Therefore, we conclude, as we generally do, correlation, not causation, so we throw it away. I'm going to argue that I think we're doing that too much. And so why would I believe that? So I show here on the bottom, this was the best of the interventional trials. Most of them were quite short, 6 months to a year. The longest one shown here was 3 years, done on people that were 67.8 years of age. Now, just to be clear, when we do the digital twin simulations, and we can simulate, again, cognition over life, there's a known mechanism for vitamin D. It attenuates the variability of the reverse cholesterol transport pathway over the decades of life. When we simulate that in the digital twins, it gives back to us what we see in the observational data. It says, yes, this would in fact lower the conversion to Alzheimer's. So that, that gives me some confidence. It's a model, but it says the mechanism would be explanatory. Now, what you can do in a digital twin simulation is you can go through and simulate the exact trials that were run. So we went back, we simulated these trials, exactly the ages, exactly the times that were followed and so forth, and said, in the simulation, given that the mechanism was totally explainable for what you saw in the observed, would we have expected any of these trials to show a signal? And the answer is no, we would not. So in my mind, then, vitamin D has not actually been tested. So it hasn't succeeded in RCT, but it also, I would argue, has not actually failed one. So the point that I really want to come to, so in the models, we can simulate then. This is a complicated plot, and there's just a couple minutes left. But basically what this is showing is just that time is much too short in order to have an effect. You would actually have to watch in those trials about 10 years before you would see separation, whereas on the right, the observational trials are long enough. So the big point that I want to make then in terms of clinical trial design is I think that the way that we do preventive clinical trials is really suboptimal. And the way that I think that we do this that makes no sense is because the current paradigm, we tend to run a blinded randomized clinical trial, that's good, but we always test one compound. When you do the digital twin simulations, is that one compound is almost never effective. And the one compound, because what are you doing? You're actually just depending on sheer dumb luck that that compound is the final piece of the puzzle, right? The vitamin D attenuation doesn't matter if you don't have phosphatidylcholine, you have no substrate for the pathway, if your inflammation is over, like it's not enough. It's a small piece of the puzzle. And so what we find then is that if you do a different method, where instead of testing a compound, what we're going to test is the digital twin model itself, right, the algorithm. So you can test the algorithm. This lets you test still one thing, so you're not getting into all the squishiness of things changing all the time as you're going through, but you can test one element, but it's complicated. It's a complex object. And what that means is you can take the model, you take a person's individual data, and every individual will get their own individualized combination. So again, you're not testing a compound, but you're testing, in essence, your entire conception of what is driving the disease and how to personalize it and what you're doing. What this means then is you get a much higher effect size because, again, you're not depending on luck, you're guiding it. Your effect size is harder, your N is lower. In the case of something like vitamin D, this is crucial, or anything basically out of the natural product world, because you're not talking about a drug that's going to make billions of dollars. Therefore, the economics of running the trial that you would need is infeasible. Therefore, no one ever does it. But if you can run it this way, it shows that you would get much larger effect sizes, lower N, economic models that actually are feasible. And I think this really lets us get to a style of clinical trial that I'm excited about. And in the interest of time, I'll skip that. Thank you. I'm happy to ask questions in the break. Thanks.
Okay, continuing right along, we are going to move on to the second part of this session, which is on interventions. We have 4 speakers, and we'll start with Rob Reinhart from Boston University, who will talk to us about brain stimulation.
Hello, thank you. It's wonderful to be here. Such a fun, dynamic conference. It's a real honor to speak at this event. So I'd just like to thank my lab members and funding agencies up front. Thank you, of course, the NIH, supported our work over the years. So just one of the overarching goals, as we see it, of cognitive precision aging is to develop novel procedures, including brain stimulation procedures, to effectively slow, but ideally arrest, even reverse, cognitive decline in older people. A parallel goal for us as well is to identify parameters of those procedures that could potentially optimize them. And some of those parameters that are emerging from our lab's work, I want to underscore throughout the talk, that involve the brain mechanism, some of its features, the intervention itself, and the study population. So the roadmap for this talk is to introduce you to our theoretical framework, our technical approach, some of our current promising results, and future directions. So the approach we take to brain stimulation, neuromodulation design is grounded in really decades of fundamental systems neuroscience that views cognition as arising from synchronous electrophysiological rhythms or oscillations. So these are rhythmic fluctuations over time in brain activity or excitability that derive from an inhibitory and excitatory postsynaptic fluctuations that are evident in the cyclic changes in the local field potential, electroencephalography, magnetoencephalography, electrocorticography recordings. Functionally, oscillations are interesting because they're thought to facilitate precise but flexible brain communication and plasticity. Two of the most extensively studied synchronization motifs, they're sometimes called, is between region, within frequency, phase synchronization. So this is when two neuronal ensembles are correlated or coherent with each other across long distances in the brain. So this is an aspect of neural connectivity. Another dominant motif is within region, between frequency, phase, amplitude synchronization, sometimes called coupling. This is a measure of hierarchical relations. This is particularly when the phase of a low-frequency wave modulates the amplitude or power of a high-frequency oscillation. What's exciting now is that we have tools at our disposal as cognitive neuroscientists that can causally isolate and augment these rhythmic patterns of brain activity that are implicated in cognitive function and dysfunction. So the one of these tools in a larger class of tools is called transcranial alternating current stimulation. This is a non-invasive subthreshold neuromodulation tool that involves applying extremely weak sinusoidal electrical currents to the surface of the scalp via electrodes that induces alternating electric field gradients in target brain regions that are potentially implicated in cognitive function or dysfunction. So this is one of the safest ways to non-invasively stimulate macroscopic brain network dynamics. The upshot of about 15 years of animal research suggests that the action mechanisms are neuronal entrainment and neuronal plasticity. So I want to briefly take you through a number of years of work, a collection of double-blind, sham-controlled, randomized experiments that fall under this header, Study 1. The upshot is that we're finding frontal temporal, high-resolution, multifocal TACS can improve visual working memory in older adults. And again, I want to underscore some of the features of the mechanism that we're targeting here as being important potentially for optimizing or personalizing these procedures to get better memory benefits. So by high resolution, I'm referring to a newer technology that provides us with smaller electrodes and many more of them so we can funnel the current in a high spatial resolution manner. By multifocal, I'm referring to stimulating the brain in multiple regions of the brain simultaneously. So this is a way to modulate brain connectivity across long distances. There's two flavors of TACS in this context. Roughly the antiphase, destructively interfering or desynchronizing TACS that can impede neural integration across long distances, and the in-phase TACS that synchronizes or can facilitate neural communication between distant brain regions. And then finally, our lab's really pioneered this personalized HD-TACS approach, personalized along the frequency of neurophysiology. So we're individually tailoring the stimulation to each person's peak frequency of their dynamic long-range brain connectivity. So here's what it looks like. Here's an example. You come into the lab. We have you do this canonical visual working memory test. You see a complex real-world object. There's a memory delay. Present you with another object. Just tell us whether it's the same or different from the original. There are trials that control for arousal, vigilance, and attention. And we find what's been observed for over 3 decades, older working memory deficits relative to these 20-somethings, inferred from longer RTs and worse accuracy. We predicted in this study that this was due at least partially to an attenuation in these synchronization motifs I mentioned, specifically long-range, low-frequency synchronization across frontal temporal cortex. This is thought to instantiate the top-down control, monitoring, and coordination that's exerted by prefrontal cortex on sensory processing zones in the back of the head, as well as an attenuation in that local theta, gamma. Theta's low-frequency, gamma's high-frequency. Theta, gamma, phase, amplitude, cross-frequency coupling synchronization. That's thought to play a role in the active, ongoing storage and processing of the working memory items themselves. And that's what we found in 2019. Older people were reduced in their theta gamma phase amplitude coupling in left temporal cortex, and they were also missing that long-range, low-frequency neural connectivity across frontal temporal cortex. However, they did show intact short-range, a high-frequency synchronization across occipital temporal regions, so there was an interesting dissociation in connectivity there. We use that neural information to inform how we design personalized TACS as well as electric field models. And when so we individually personalize each person's TACS frequency to the peak frequency of their theta phase synchronization across frontal temporal cortex, that neural connectivity measure. And when we randomize older people to either active or placebo sham, we find that we can rescue both of these synchronization motifs in the brain, independent of changes in spectral power or phase-phase coupling. And behavior comes along for the ride, so we can boost cognitive performance on this working memory task by resurrecting these neurocoding motifs. But without slowing people down, RT didn't change. So we can effectively make you better without slowing you down. Incidentally, these were changes that after this just single one-shot 25-minute dose of stimulation boosted older people's working memory success so high that it was statistically indistinguishable from these 20-somethings. We also looked at brain behavior relationships, and we find that the tighter the coupling, the better your performance, the better your memory performance. That's true in young people. It wasn't true in old people at baseline, but after the 25 minutes of stimulation, we can not only revive these coding motifs, but we can imbue them with a kind of functional significance. So now they are predicting behavior on a participant level. Another experiment, this one just in healthy young adults, we sought to obtain bidirectional causal control over this neurocircuitry, apply the antiphase, destructively interfering or desynchronizing TACS, and show that we can induce rapid deficits in visual working memory. This is something that we've observed before, some years ago, this bidirectional causal control over the memory circuitry based on the phase angle of the alternating current that we're pushing and pulling through the system. So here we can up or down regulate learning and adaptive behavior in healthy young adults, again, based on phasic relationships with the TACS. And we're also observing that across laboratories across the world, researchers are observing a similar pattern: in phase, improve, antiphase, impair. This is the largest meta-analysis to date. We recently published another experiment. We replicated the principal behavioral findings in an independent cohort of older people and extended them, looking at spatial and spectral specificity of these behavioral benefits induced by this personalized TACS. The upshot here is that you can't just stimulate anywhere on the brain and see these effects, nor can you stimulate within the regions of interest independently and see these effects. You have to stimulate simultaneously, at least for domain, paradigm, stimuli. More evidence to suggest that we're really locking into a manipulation of connectivity. In terms of frequency, you can't just stimulate any frequency on the brain and see these kinds of behavioral benefits, nor can you stimulate within the frequency band of interest, theta band. The personalization is essential. So we're finding that frontal temporal HD TACS personalized to each individual's brain network dynamics can improve visual working memory in older people, at least in this proof of concept study. And we're identifying personalized theta frequency, 0 degrees phase lag, and left frontal temporal regions as potentially particularly important for optimizing procedures like this. Here's another collection of double-blind randomized sham-controlled experiments falling under study 2. The bottom line here is that what's emerging is a frontal and parietal HD TACS may have a preferential improvement on, this time, auditory verbal working memory and auditory verbal long-term memory in older people. And again, I'll underscore as I go a number of parameters I think are important for optimizing these the TACS. So we've known for almost a century from experimental psychology that if I read you a list of words and you recall freely back to me as many words as you can, you have an advantage for the words early on that list, deemed the primacy effect linked to long-term memory, at least on the classic dual store framework. And you also have an advantage for the words later on that list, deemed the recency effect linked to working memory. We know quite a lot about the functional neuroanatomy of primacy and recency serial position curve effects. For example, that the inferior parietal lobule is a major player in recency, working memory, and the dorsolateral prefrontal cortex is a major contributor to primacy. However, what we don't know is whether there are distinct rhythmic mechanisms within these segregated cortical regions that subserve these memory functions. But if there are, and they can be identified, then we could potentially bring TACS to bear to selectively and independently manipulate these mechanisms and these memory systems. And that's precisely what we set out to do in this series of experiments headed up by Dr. Sheree Grover, postdoc in the lab now. We designed 2 novel high-definition TACS procedures. In this time, we were interested in really trying to sustain the memory benefits over the long term, so we repeated the stimulation every day for 4 days in a row. We measured memory performance before the intervention, every day of the intervention, 1 month post. And the upshot here is that we're finding a double dissociation between the spatial and frequency components of the mechanism on the one hand and the memory system being manipulated on the other hand. So on the bottom in the orange, on the left in the red box, you see that when we apply low frequency, but not high frequency, entrainment to parietal cortex, but not prefrontal cortex, we can induce significant improvements in auditory verbal working memory, the recency effect, on day 3, day 4, and 1 month post. And in contrast, when we apply the high frequency, but not the low frequency entrainment to prefrontal cortex, but not parietal cortex, we can cause long-term memory, primacy, improvements on day 2, day 3, day 4, and 1 month post. So this is the aspect of the dose or duration feature that I wanted to underscore. Just notice like how many days it takes for this significant memory benefit to come online. We did something unique here where we actually acquired memory performance data during the intervention itself, which is seldomly done. That allows us this opportunity to evaluate how people are responding to the intervention, the memory benefits that they're experiencing itself. And we found that the steeper that rate of improvement in memory performance for both primacy and recency, the bigger the benefits were 1 month later. We also find that baseline general cognitive performance as measured by the MoCA was a significant predictor of how people responded during the intervention and how large and enduring those memory benefits were 1 month after the intervention was over. That's what I meant by cognitive status of the study participants as being an important feature. At the meta-analytic level, there's been only a paucity of studies, but if we look at all of them, in older people using TACS on various cognitive domains, we see promising results, modest to moderate-sized effects. We really think these are being kind of undersold, underestimating the really power of this procedure because there's a small number of studies to date, and the vast majority don't personalize the stimulation. They're not multifocal. They're not high definition. So we've developed 3 novel HD TACS procedures to improve visual working memory, auditory verbal working memory, and auditory verbal long-term memory in older adults. These are, of course, more proof of principle studies. There are a number of open questions. Of course, some of them relate to demographic variables and how it interacts with these memory improvements. Our samples were representative in terms of race, ethnicity, and biological sex of the greater Boston metropolitan area, which is not too different from national averages. And just want to highlight again that phase, frequency, and space information of the mechanisms we've targeted appear to play an important role, as well as the dose or duration of the intervention and the cognitive status of our participant population. There's a number of future directions I'd love to talk about. One of them relates to Alzheimer's disease, current clinical trial that we're running in my lab now. So I'll just share some preliminary data. Don't want to overinterpret a small n, it's just n of 10 here, but it's kind of titillating and new data. So we're seeing these, drastic memory capacity deficits in MCI and AD patients, particularly at larger set sizes. And here we're finding that just with a single 25-minute dose of this personalized brain stimulation, we can go a long way in rescuing memory capacity in people with MCI and mild AD, particularly at larger memory loads where their deficits are greatest. Thank you.
Thank you, Rob, for a fascinating talk. So up next we have Frank Lin, who just came down the street from Johns Hopkins, and he'll be talking about hearing interventions in the ACHIEVE trial.
Good morning, everyone, and thank you again for all of you for being here, and especially to the NIA and Ignite Foundation for sponsoring this. So I'm going to be presenting today a trial that was resulted out in the Lancet last year, and specifically talk about the heterogeneity of treatment effects. So it's going to be a broad overview of the study, but really focusing on the primary result and how it really differed among study populations. As all of us here know, science is a team-based sport. For a multi-site clinical trial, this really holds true. So it's really, I'm presenting here on behalf of a much larger collaborative group, 8 institutions, working together for the last 10 years through the generous support of the NIA. All right, so brief background, what we studied and why. This figure has been shown before, the Lancet Commission on Dementia identifying putatively modifiable risk factors. Interestingly, hearing loss in mid and late life identified as a single potentially largest modifiable risk factor based on a population attributable risk or a populational fraction of risk. The reason for this is because the epidemiologic studies linking hearing cognition have shown very large risk ratios, and you multiply by that hearing loss is a very, very, very common prevalent condition as everyone ages. For those of you who don't know about hearing, it's essentially a monotonic condition beginning after your teenage years. Everybody's hearing slowly and monotonically decrease over your entire lifetime. And it's because the inner ear is post-mitotic. So various rates depending on age and demographic and genetics, but everyone loses hearing over time. All right. More importantly, we say it's potentially modifiable, though, is because of these putative mechanisms linking basically greater levels of peripheral hearing loss with increased risk of cognitive decline dementia. Now, keep in mind, as all of us develop hearing changes, hearing loss as we age, it basically means you're getting a much more garbled auditory signal sending to the brain. So the brain literally needs to basically work a bit harder to decode that signal. So one mechanism idea of cognitive load is the brain constantly reallocating resources to help with hearing, and then come at the expense of other systems. So getting at the idea of very much cognitive load and tapping into cognitive reserve. There's not a resource to buffer against other pathologies that are contributing to dementia. Either that or direct effects of hearing loss and direct effects on brain structure and function. We actually see that in epidemiologic as well as animal studies now. And find the idea of social isolation or loss of cognitively stimulating activities. Now, the reason why these mechanisms are important, of course, though, is because it suggests, theoretically, if you treat, could they in fact modify these pathways and reduce the risk of cognitive decline dementia over time? So the ACHIEVE trial was really designed to answer that just really simple question. Namely, if we treat hearing loss in older adults, can we in fact reduce cognitive decline within 3 years, a relatively short period of time, basically among older adults otherwise cognitively intact? This is called the ACHIEVE trial. The main outcome is global cognitive decline. I'll go over in a second what I mean by that. There are a bunch of secondary exploratory areas, which I won't go over today, but I will show you some of the preliminary results of the MRI data. All right, so briefly about study design, conceptually simple. So 977 older adults, 70 to 84 years old, mild to moderate levels of hearing loss, otherwise cognitively intact. Interestingly, they were recruited from 2 distinct study populations. This is important. About a quarter of the cohort of 977 came from an existing observational heart health study called the Atherosclerosis Risk and Community Studies. I'll go over that in a second. I'll go over that in 1 second what that is. And the other 3/4 came from de novo, newly recruited community volunteers recruited through advertisements, Facebook ads, radio ads, and things like that. Those 2 study populations comprise a total cohort. They were then randomized to a hearing intervention versus a control intervention. I'll go over what I mean by those in a second. Then followed annually, actually every 6 months for the next 3 years. Primary outcome 3 years later being global cognitive decline, and a host of other exploratory outcomes as well. Now, I mentioned this before, so the ACHIEVE study, as any of you have ever had to do a multi-site trial, they're hard to get set up, so whenever you can leverage existing resources, it makes it a lot easier. In our case, we partnered with a study called ERIC, the Atherosclerosis Risk and Community Studies. This is a study that's been going on for over 30 years, funded by NHLBI. They recruited basically in midlife, 30 years ago, midlife adults from a random sample of the population, recruited through voter registration polls, driver license record polls, and basically recruited them into the study looking at midlife cardiovascular risk factors and later life cardiovascular disease. So they've been followed for many, many years. So about a quarter of the sample came from existing ERIC participants who we could pre-screen because we knew their hearing levels, we knew their cognitive levels, and we invited them into the study. The other 3/4 of the cohort came from the same communities, but were new volunteers. Literally, people responded to Facebook ads, radio advertisements, TV ads, and things like that. So again, 1/4 from ERIC, representing a random sample of the population, 3/4 from newly recruited older adults at these 4 different ERIC field sites that we utilize our existing personnel infrastructure. The actual intervention, people were randomized, flip of a coin, basically. They got a hearing intervention, basically best practices, 4 visits with a study audiologist over the first 3 months of the study where they got hearing aids, any other technology they need to basically hear well, and they're shown how to use it. The other half of the study got an education control intervention, so basically meeting a one-on-one with a health educator going over topics like nutrition, diet, exercise. So they're all time matched for exposure to study personnel. But one group obviously got their hearing addressed. The other group basically got general education counseling on critical healthy aging topics. Again, so 4 sessions over the first 3 months, every 6 months, a booster session and a follow-up visit thereafter. The actual cognitive battery, it's a 10-test neurocognitive battery. It's about 45 minutes, administered by a psychometrist trained by a neuropsychologist. Just briefly, these are the 10 different neurocognitives that have been long used in ERIC. From that, we derive 1 global cognitive factor score, so sort of like a Z-score, but allowing for individual item and test weighting to get a more precise measure. But we get 1 global cognitive factor score. That global cognitive factor is standardized to baseline. So if your score is 0, it basically means you're right smack dab in the middle at mean, at baseline. If you're 0.5, it means you're half a standard deviation away from that group mean. If you're negative 0.5, it means you're negative half a standard deviation away from the group mean. Likewise, the way you interpret change over time, if you change by negative 0.5 over 3 years, it means you've declined by half an SD unit over a 3-year period. You can also extract domain-specific cognition from these different tests as well. Language, this is language production, not language reception, basically category and semantic fluency, executive function, and memory. Importantly, what I want to emphasize, though, is 8 of these 10 cognitive tests are not auditory exclusive. So if someone's not doing well on a cognitive test, I can assure you it's not because they're not hearing well. These are basically visual and auditory or visual instructions only. For the 2 tests that are auditory only, even before we administer that test, we actually verify their speech understanding. And what I mean by that, they read a list of sentences, and we actually document how well they can repeat the words back correctly to make sure it's not being confounded by not being able to hear well. Again, for mild to moderate levels of hearing loss with a psychometrist, face-to-face, arms like the way in a quiet room, you wouldn't expect that to affect auditory reception at all. But just theoretically, we controlled for it, we adjusted for it, and we essentially assured there wasn't an issue beforehand. And again, most of these cognitive tests are non-auditory to begin with. All right, the recruitment period, we began recruiting in January 2018. This I'm always very proud of. Line is if we had hit 850 right on target. We're 2 weeks behind schedule with recruitment when we hit 850. Because of how well recruitment was going, we kept it open for a little longer, so we actually kept it for another few more months with the support of the NIA and then the DSMB support. So we ultimately got to a sample size of 977 in October 2019, 5 months before the pandemic hit. So we got lucky, and what I mean by that, the study was very fully recruited. Everyone had already received their primary intervention before the pandemic began. The reason why that's important is because after the pandemic began for about a year period, we could not do in-person visits. So we could only do putatively phone-based visits. But importantly, 3 years later, all the baseline and all the year 3 visits were all done in person. So the neurocognitive results you're seeing today are all done in person, not phone-based neurocog. Baseline, year 3, all done in person. Something that we're hugely proud of, too, is a testament to the quality of the study staff, is that after 3 years through a pandemic, fully have complete data on 90% of people between 70 and 84 3 years later. So we had attrition about 10%. Some people died, some people moved away, unfortunately. But overall, this is something we're very, very proud of, this number after 3 years. All right. This normally is a table I would show stratified by intervention versus control. I can show you those are basically equal because it was randomized. What I'm showing you here, though, which interestingly, though, is the baseline characteristics stratified essentially by the recruitment source. Basically, people came from ERIC versus de novo. And the first thing you'll notice is that on average, the de novo cohort has fewer risk factors for cognitive decline dementia than the ERIC cohort. Remember, ERIC being sort of a random sample of the population, de novo being self-selected healthy volunteers. And you see that study population source being reflected in these characteristics. So you see on average, the de novo cohort is slightly younger, 76 versus about 79 years old. Black race is interesting. The reason why it's such a skew there is because ERIC, specifically 1/4 of all of ERIC was fully Black American. Everyone recruited Jackson was all Black. So you're seeing that reflected there, whereas the de novo, you're seeing much of a sort of relatively a sample of community volunteers. That's why you're seeing discrepancy there. But on average, again, education, you're seeing that on average, the de novo cohort has higher rates of education, higher rates of income as well. And again, this makes sense. A self-selected population is going to be different than a randomly recruited sample of the population. You're also seeing that in cardiovascular risk factors. You see on average, the de novo cohort has lower rates of diabetes, 17% versus 28%. Been on hypertension as well, living alone. You're seeing less living alone in among the de novo versus the ERIC cohort again. Now, what's interesting, if you look at the baseline cognition, again, these are standardized factor scores. You see on average, the de novo cohort, global cognition, they're about 0.12 standard deviations above the mean, whereas the ERIC cohort starts below the mean relative to the total average. Again, so you're seeing this baseline difference in cognition, again, among a self-selected group of healthy volunteers versus a random sample of the population. All right, so I'm going to jump to the 3-year cognitive outcomes now. This is a busy figure, so I'll take you guys through it slowly. Top left there, what you're seeing there, the control group, after 3 years, who got the control group, you see on average that the control group declined by 0.202 standard deviation units in terms of cognition. If you look at the hearing intervention group, 0.200, essentially the same. So the primary outcome among the total cohort, you're seeing no differences in rates of cognitive decline over 3 years among hearing intervention control. So putatively disappointing at first. If you look at the 3 secondary outcomes, executive function, language memory, basically the same thing. Maybe of a signal memory being a protective effect with hearing intervention, but clearly nothing at home to write about. Now, what gets a lot more interesting, though, is one of our pre-specified sensitivity analyses, pre-specified literally 5 years when we designed the study, is that we always said we would replicate the primary analyses stratified by the 2 different study populations. Because we recognize that a random sample of population from ERIC versus a self-selected healthy volunteer group may be right? We didn't quite realize how different they would be, but this is what you're going to see. So among the ERIC cohort, again, the people who were representing a random sample of the population, you're seeing very, very strong effects of hearing intervention reducing rates of 3-year global cognitive decline compared to control. You're actually seeing technically about 48% relative reduction in rates of cognitive decline. You see that in the top left there. Control group in ERIC declined by 0.40 standard deviation units versus hearing intervention declined by 0.211. That's a 48% relative reduction, about a 0.2 absolute difference in 3-year rates of cognitive change. But if you look at the de novo cohort, you're seeing no effect of the hearing intervention on slowing cognitive decline. So why? And if you look at the data a little more clearly, it becomes sort of clear. Whoops. There we go. If you look at the rates among the control group of 3-year cognitive decline in the ERIC cohort, again, 0.402 standard deviation change over 3 years. In contrast, if you look at the de novo controls, they only decline about 0.151. So you're seeing essentially a 3-fold slower rate of cognitive change over 3 years among the de novo controls versus the ERIC controls. And remember, again, the de novo controls were self-selected, new healthy volunteers at baseline having many fewer risk factors on average for cognitive decline dementia than the ERIC cohort. So it's being reflected directly in the sort of the baseline rate of cognitive change. So one way of interpreting this is that a hearing intervention is predicated on reducing cognitive decline. And if you're having among the de novos very, very little cognitive change over 3 years, you can't slow down something that's not really declining to begin with. In contrast, the error controls having a much faster, nearly threefold faster rate of cognitive change, there's actually room to slow that down within, or observing within just 3 years. Now, what's interesting, I'll show you some exploratory effects now, looking at brain health and brain MRI data. And this is predicated, again, on the main mechanism. There's 3 major mechanisms linking hearing and cognitive decline dementia, basically one of them being effects on brain structure. So do we, in fact, see a signal that hearing intervention is reducing rates of brain atrophy, cortical thinning, within just 3 years? So again, this is exploratory. This is not power to look at this, but I'll just jump to the data. So this is, we had MRI data on half sample. About 445 to 977 had MRIs at baseline, and a subset had baseline MRIs 3 years later. This is cortical thickness. So this is cortical thickness in each lobar region. This is all extracted by Cliff Jack's group at Mayo, his Alzheimer's Disease Imaging Research Laboratory. And what you see here again is, again, this is exploratory data. We're not extracting p-values necessarily. These are all sort of observational effects, or I say exploratory effects of what intervention may do. But what you clearly see here is a very clear general trend toward a protective effect on reduced cortical thinning within just 3 years. We were actually, I shouldn't say that, I didn't think we see anything. And technically, I guess you're not. It's exploratory. But we were seeing a very, very clear signal within just 3 years of reduced cortical thinning with hearing intervention in a randomized controlled trial across multiple different brain lobar regions, actually the smallest effect being the temporal lobe, which is actually where a lot of auditory processing is. Now, I'm going to show you one other follow figure. This is a region of interest analyses now. Again, using the same data as before, looking at cortical thickness within each ROI. The red is where there's reduced cortical thinning over 3 years with hearing intervention, versus the blue is theoretically increased cortical thinning. The level of the color indicates a degree of reduction or increase. And what you're seeing here is broadly, you're seeing very, very strong signals in certain areas, specifically the cingulates, especially the anterior cingulate, very critical for really sort of the intersection zone of auditory processing, cognitive processing. And some of the strongest signals actually look in the frontal lobe, the pars orbitalis, which is a critical area for language processing. So we're seeing very, very strong signals again. This is an exploratory outcome. We're not powered to look at this, but very encouraging for clearly seeing a signal in reduced cortical thinning, again, within just 3 years in a RCT with essentially a hearing intervention and basically hearing aid use. Brief summary. So I'll say again, in the total combined cohort, right, we're not seeing an effect of hearing intervention reducing cognitive decline within 3 years. If you look at the pre-specified analyses stratified by the different study populations, these things are very, very different. In ERIC, again, representing a random sample of the population, seeing about a 48% relative reduction in cognitive decline. The absolute reduction is 0.21 versus negative 4.02, so about a 0.2 SD unit difference over 3 years. And from this, you might extrapolate that hearing intervention may, in fact, reduce cognitive decline, but specifically among populations that are actually experiencing cognitive decline. In contrast, no effect observed in the de novo, again, but a very, very slow rate of baseline cognitive change would probably limit your ability to detect any further slowing of something that's not really declined to begin with. And finally, exploratory MRI analysis suggests a potential biomarker effect. What I'm not showing you here is all the other effects on socialization, loneliness, where you're seeing very, very clearly positive effects within 3 years. Last slide. Possible explanations, again, for the slow rate of cognitive change among de novos is one is clearly a healthy volunteer effect. I think you're seeing that's known epidemiologically. Another reason came earlier today with Kristine Yaffe's talk is prax effects. De novos, you're going to see prax effects. They are cognitively testing naive. ERIC, interestingly, these people have been tested cognitively every few years for the last 30 years. You're not seeing prax effects anymore in ERIC. At least you wouldn't think. If they've been tested for cognitive testing every few years, every 30 years, you might be seeing a truer rate of cognitive change because you're not seeing prax effects. Last two extrapolations that are, I think, important for discussion later. Study populations matter a lot. We think about this for drug studies. You think about enriching for certain biomarkers. I think it's given less thought for essentially behavioral interventions. How do you actually enrich, per se, or get populations that really are representative? Final last thing, implication of cognitive testing, if you're thinking about cognitive change being the primary outcome, is that prax effects really, really matter. I'll finish up there, and thank you all for your time.
Thank you, Frank. Moving right along, our next speaker is Julie Wetherell from UCSD. She will tell us about the MEDEX study.
Great, thank you. And I want to thank Molly and John for inviting me to present at this conference. This has been enormously educational. I also want to thank NIH and the McKnight Foundation for funding the study that I'm going to talk about today. So in both the research literature and the popular press, both exercise and mindfulness-based interventions have gotten a lot of attention as potential preventative or remediation interventions with respect to age-related cognitive decline. And there are a number of potential mechanisms for this with respect to exercise, insulin sensitivity, reductions in inflammation, changes in oxygenation, neurotrophic factors, et cetera. With respect to mindfulness, the biological basis that's usually proposed is HPA axis reducing the hyperactivity as measured by cortisol. With respect to cognitive factors, perhaps increased attentional control and also some emotion regulation improvement as well. So my background is I'm a clinical psychologist, and I've done a lot of work with behavioral and psychotherapeutic interventions for older adults with anxiety disorders. And I've been working with Eric Lenz, who is a geriatric psychiatrist at Washington University in St. Louis, with older adults with anxiety, and we developed an interest in mindfulness and decided to do a study looking at older adults with either diagnosed anxiety disorders or depression who were also reporting subjective changes. And we randomly assigned them to either mindfulness-based stress reduction or a health education control condition. And we found that relative to health education, we actually saw improved memory performance associated with mindfulness-based stress reduction, and some evidence that the reduction in cortisol might be the mechanism. So among those folks with cortisol at baseline, reductions were associated with the receipt of MBSR relative to health education. So using those as, using those as pilot data, we did, funded by NIA and the McKnight, a larger study in which we also incorporated exercise. So we're looking primarily at the effects of mindfulness-based stress reduction, a multi-component exercise intervention. We were also going to look at some of the proposed mechanisms, so looking at cortisol as a measure of HPA axis hyperactivity, looking at increased aerobic fitness, insulin sensitivity, and BDNF. We were doing brain imaging to look at both structural and functional connectivity. And then finally, kind of the most distal outcomes, any impacts on cognition, specifically memory and cognitive control, also known as executive function. So our exercise intervention included aerobic activity, which is kind of in line with our hypotheses, but we also included strength and balance and mobility training because that's kind of the ideal package of interventions for older people. Initially, for the first 6 months, these people met in groups of twice a week in groups of about 15, and then once a week after that through an 18-month period. Plus, they were assigned home exercise with a goal of exercising 300 minutes a week. And these were individually tailored exercise prescriptions. So people came in, they were sedentary initially, and they increased their the difficulty, the intensity as they went through the study. Mindfulness-based stress reduction, many of you may already be familiar with this. This is a program developed by John Kabat-Zinn. It's kind of a protocolized training in mindfulness. It includes meditation. It includes yoga. It's taught in 8 2.5-hour weekly classes, and then we added monthly booster sessions again out to the 18-month duration of the trial. Daily home practice was assigned with a goal of up to 60 minutes per day of meditative practice. And then we used health education as a comparator condition. And this was actually based on the Stanford Healthcare Self-Management Program, which has been the subject of a lot of research in and of itself. It's designed to improve healthcare self-efficacy, not designed to improve cognition. It talks about exercise, it talks about mindfulness, but doesn't teach those techniques. But there are personal goals, and I'm thinking, of course, of Dr. Jaffe's talk. This was a very tailored program where somebody might have, the goal of working on their diet, or they might have the goal of managing and monitoring their blood pressure, these kinds of things. We did intend it as an attention placebo, so it was matched for the MBSR in terms of the setting and the time, but we tried to keep the specific content limited. So this is just basically a graph showing our research design. 18 months total. People were assigned for the first 6 months to either MBSR alone, exercise alone, the combination, or the health education. Our study population was intended to be 580 people, 65 to 84. With reporting subjective cognitive changes, but no diagnosed dementia, no mild cognitive impairment. They also were not diagnosed with diabetes because we were looking at the insulin sensitivity. They completed a very large battery, including neuropsychological tests, biomarkers, metabolic and fitness measures, imaging, and behavioral and functional measures at baseline, following the 6 month, which was our main time period, and at 18 months. And then we also had some neuropsychological testing at 3 months as well. And the outcomes that I'm going to talk about today, our primary outcomes are cognitive. So we made composite scores, kind of what Dr. Lin talked about in terms of for memory and cognitive control. We had paragraph and list learning, immediate and delayed, and then some measures from the NIH toolbox, which Dr. King mentioned yesterday, for cognitive control, and then a couple of other computer-based tests of cognitive control or executive function. Our sample, we actually over-recruited a little bit, which is always good. Our sample was kind of young, old, 71.5 years on average, very much female, and mainly non-Hispanic white, which is, again, what kind of healthy volunteer sample that Dr. Lin just talked about, of normal cognition to start. They did mostly have at least some college. They were largely healthy because they had to be healthy enough to be randomizable to a moderate to high intensity exercise program. They did have medical illness, on average 3, the most common. A third had hypertension, and then also osteoarthritis and hyperlipidemia, but a number of other things as well. And they did, on average, have impaired insulin sensitivity, although we didn't recruit for that. And the bottom line is this was a null results trial. We did not find, in our study at least, that either exercise or mindfulness or the combination had an impact on cognitive function or brain volumes. We did find some marginal effects on the functional brain, which I'm not going to talk about, but it has been published. But generally speaking, we had to do a little bit of digging then to try to figure out why this study did not work as we had intended. But just to present a little bit of data, what this looks like, on the left side, we see the graph of people who either received or did not receive MBSR, the cognitive changes over baseline through 18 months. We did see an initial improvement, which could have been a practice effect, although we did do what we called a baby neuropsych battery within 2 weeks before their baseline to try to get these older folks at least familiar with sitting down at a computer and taking some of these tests. But they improved the same amount with or without MBSR and with or without exercise. And I don't have a graph, but the same was true. There were no interaction effects. Cognitive control, the same story. We did not find any effects for MBSR or exercise, although the pattern was a little bit interesting here just in terms of there was improvement in both groups up through 6 months, and then people kind of stabilized thereafter. So trying to figure out why. And the first question is maybe people weren't adherent. Maybe they weren't actually doing the things that we were recommending that they do. So in terms of adherence, we looked at class participation, which was very easy to measure, and the vast majority of people in all three groups attended at least 70% of the classes. So, with respect to class participation, we had pretty good adherence for a study of this type. We collected at-home practice information, self-report weekly while the folks were in the exercise class, or weekly or monthly while people were in MBSR. We also had 3 periods where we did ecological momentary assessment, where we pinged people 3 times a day, and in the morning, for example, we asked them about sleep. In the evening, we asked them about their practice. So we did get some data that was hopefully a little bit more reliable. And as the histograms at least show that people did report home practice, and most reported quite a bit of it. So looking at the folks who were the whole sample overall, you see on the left, you've seen that graph, no differences with folks who either did or did not receive MBSR. On the right-hand side, this is a subset of the folks that reported home practice on at least 70% of days, and again, no differences between the groups. With respect to exercise, again, the same pattern. On the left, the entire sample, no differences. On the right, folks who reported exercising on at least 70% of days, and no differences between the folks who received the exercise intervention versus not. So the next question is, well, maybe we didn't engage the target. Maybe the exercise, wasn't intense enough. Maybe we weren't actually making a difference in our interventions. So we looked at, a lot of different indices, both physiological and performance variables associated with exercise. And we actually found that the exercise group did have better insulin sensitivity. They had better aerobic fitness, strength. We got the sleep variables actually not only through the self-report, but we had them wear actigraphs, so we got some actual objective data on their sleep. And exercise turned out to be beneficial for all these things. So great. In contrast, we did not see any effects of MBSR, not even state mindfulness. So I don't know exactly what was happening there, but we then looked at, this is the memory composite change in the folks who got exercise, and we're comparing the people who had the most improvement in their insulin sensitivity versus the ones who had the least improvement, and again, no significant differences. So target engagement did not appear to be a factor, and we looked at this many different ways. I'm just showing you an example here. So when you get results like this, okay, so was this genuinely a negative result, or was it a failed trial? And I would argue in some ways, I think we were pretty successful. You could say, well, how were the outcomes? We actually found that the cognitive composites had a good reliability, about 0.8, which is reasonable. Poor adherence, I already showed those data that people were pretty well adherent. And the folks who were more adherent looked pretty similar to the folks who, the overall sample. Were the interventions too weak? Well, the exercise group did what exercise should do in a group of sedentary older adults, at least in terms of some of the outcomes that we would expect for physical health. Not so clear with mindfulness. And again, those who showed evidence, objective evidence of improvements by exercise, had similar outcomes versus those who did not. So perhaps it was the wrong type of intervention. Might have been too soon. These were cognitively healthy, normal adults, not on a decline trajectory yet, perhaps. Too late. We've heard lots and lots about needing to start some of these interventions or, behavioral changes in midlife or earlier. So the fact that we waited until they were older might have had an impact. Too short. This was 6 months of relatively more intensive intervention, although it was 18-month trial. But, hearing about 3-year interventions and longer interventions, it's possible that that was an issue. Too low intensity. Yeah, I don't know about that. I mean, we kind of designed this to be, what was recommended in terms of both exercise and sort of standard protocol for MBSR, but it's possible that that's not enough to improve cognitive outcomes in older people. So here's, one of the issues, I think, failure of recruitment. So I think this came up most clearly, obviously, in Dr. Lin's study. Oops. These were largely healthy participants, so they were required to be sedentary, and we had a number of questions to try to elicit that information. But they had to be obviously randomizable, so they had to, and they also had to not have diabetes and kind of some more other sample or some other criteria. So they were pretty healthy. Remember our pilot study, which showed an impact of mindfulness-based stress reduction, was in older adults with anxiety and depression. We did not screen out people with anxiety or depression. Very few of these folks had significant levels of anxiety or depression. Sorry about that. These were, again, this volunteer sample, largely affluent, which means they had good access to health care throughout their lives, good nutrition, a lot of privilege factors, basically, that may have affected our results, and cognitively intact to start with. And I said in both of these studies, we recruited for people who were reporting some kind of cognitive change. But the question is, what does that represent? So in some of my other work with anxiety, older adults with anxiety disorders, often people who report cognitive changes are more anxious or depressed as opposed to actually in the early stages of decline. But I think in this case, we might have had folks who were very attentive to things like their cognition, their health, and they were already engaged in a lot of behaviors to take care of their health. And again, that might have given us not enough room for improvement. So in conclusion, we did not find cognitive benefits with these interventions. It casts some doubt on the interventions, at least as implemented in this study, and their mechanisms in a healthy volunteer older sample. I think going forward, it's important to do research with more vulnerable and more diverse samples of older adults, potentially with more potent interventions, and definitely looking at longer-term interventions and maybe looking at prevention over time, which is what we're in the process of doing right now. We're continuing to follow these individuals and looking at sort of their, whether we are able to keep them cognitively healthier longer. So with that, I just want to thank these huge crowds of people in both St. Louis and San Diego, without whom we could not have done this work, and look forward to questions later. Thank you.
Okay, and our final speaker of the session, Arnold Bakker from Johns Hopkins, and he'll tell us about hippocampal hyperexcitability and the HOPE-4 MCI trial.
Thank you. Let's see if I can figure this out. This has been an absolutely wonderful and stimulating meeting, and I want to thank the NIA and the organizing committee for giving me the opportunity to present some of the work that we've been doing in the lab, which is really focused on trying to understand the difference in aging trajectories, as I know many of you are focused on. If you take rats and you put them in a water maze, you quantify their memory performance on task, we see clear differences between aged groups and young animals, with the aged showing a wider range and bigger variability in their performance. And the interesting observation that some aged animals will perform equivalent to their young counterparts, whereas some animals do not. They show an impairment on this particular task relevant to their young counterparts. And you can use this observation to define these groups, the aged impaired and the aged unimpaired. This is obviously not limited to rats. On the right-hand side at the bottom, I'm also showing a graph that was obtained from a memory paradigm using primates, and we see the same increase in variability, with some animals performing similar to young animals and some animals not. And of course, on the bottom right-hand side, I show data from human subjects where we all know that this is the case. There's huge variability in these trajectories. And the key question is, what differentiates the successful agers from the not successful agers that show impairment? And of course, as we've learned, particularly at this conference, there's many different factors that contribute to these differences in trajectories. In my lab, we're really focused on trying to understand the major contributing factors that contribute to memory impairment. So if you focus on memory impairment, and you take those two groups of animals, the aged impaired and the aged unimpaired, I'm going to focus here on the aged impaired compared to the young, and you do single-cell recording in hippocampal place cells when they're navigating through familiar and novel environments. As you can see here on the left-hand side, you see an interesting observation. We know from recordings in young animals that the CA3 very rapidly creates a new place field representation of a novel environment, and when you put the animal back in the old environment, the old representation comes back. But in the aged, in the bottom row, you can see that there is a rigidity in the firing pattern that is observed in these aged impaired animals. There's a failure to update or to represent the novel environment, as is quantified in the bar graphs on the bottom right-hand side. And this is specific to the CA3 in the aged impaired animal. We do not see that in the CA1. What's quantified in the bar graph at the top right is the firing rate. In addition to the rigidity in the firing pattern, we're also noting an increased firing rate in the aged in both the novel and the familiar environments. That is something that is not seen in the young animals. So this, in addition to a lot of other data, led to a model of neurocognitive aging that was proposed by Wilson and colleagues back in 2006, proposing that a loss of input from the entorhinal cortex into the hippocampal circuitry, and as well as hyperactive neurons in the CA3 as a result of the audio-associative projection on the recurrent collaterals, the imbalance of that activation results in memory impairment, or at least contributes to memory impairment that we're seeing in these animals with that rigidity in the firing pattern specific to the CA3. In human subjects, so switching over to human subjects right now, there's been some evidence of this hyperexcitability in the hippocampus as well. Brad Dickerson at Harvard University published a paper in 2005 showing that participants with mild cognitive impairment show hippocampal hyperactivity that was not seen in the control participants, and it's also not seen in patients with Alzheimer's disease dementia. This particular study did not have sufficient detail to locate that hyperactivity to the subregions of the hippocampus. This study was done later by Dr. Magyasa here, who repeated that study with high-resolution neuroimaging methods, and I'm showing here at the bottom right-hand side that hyperexcitability or that hyperactivity can be localized to the left CA3 dentate gyrus subregion of the hippocampus. It is not observed in the CA1, and it's not observed in the subiculum. On the left bottom-hand side, I'm showing that this is in the context of a memory impairment in episodic memory performance that is highly dependent on this hippocampal circuitry. So that raises an interesting question. Whereas Dickerson in his paper suggested that the hippocampal hyperactivity observed in patients with MCI was compensatory, it was an attempt of the hippocampus to make up for loss, these data suggest that the hyperexcitability might in fact be contributing to the memory impairment that these participants are experiencing. So then that raises a hypothesis: does reducing excess activation observed benefit or impair memory performance? If it is compensatory, reducing it would make memory worse. If it is in fact part of the problem, reducing it would improve memory function in these participants. We're going back to the animal model at this point. This was work done by Ming-Teng Ko at Johns Hopkins. He tested this hypothesis in this animal model using a systemic low dose of levetiracetam, which is an anti-seizure medication, which is of course intended to lower or normalize aberrant excitation. And you can see in the bottom left-hand side that in specific doses of levetiracetam, 5 milligrams per kilogram and 10 milligrams per kilogram, successfully reduced the number of errors on this water maze performance. On the right-hand side, you can see that they are in fact on levetiracetam, spend more time in the target quadrant of the escape platform than in the saline control condition. So then obviously the question becomes, again, if we switch back to human subjects, does this hold as well? Levetiracetam is an FDA-approved treatment for epilepsy that's been around for many years, so we can test this hypothesis in human subjects as well, and that was done in a proof-of-concept study entitled Bridging Cognitive Aging in Rodents to Man using fMRI and amnestic MCI. I'm showing the design of the study here on the right-hand side. This is a within-subject crossover design. MCI patients were initially assigned to a drug condition. They completed drug treatment for 2 weeks. Those who were initially assigned to drugs would then complete a washout period and then be assigned to the placebo condition and repeat another 2 weeks of treatment. Those who were initially assigned to placebo would complete the washout and then transfer over to the drug condition. Age-matched controls were also enrolled in the study, and they were on placebo, single-blind, obviously, throughout the duration of the study. We enrolled 54 MCI patients across 3 different doses of the drug and 17 age-matched control, and these are the results of that proof-of-concept study. So the left-hand bottom bar graph shows the 62.5 milligram dose, which is the equivalent of the 5 milligram dose in animals. And you can see that across the 3 cohorts, so the middle is the 125 milligrams and the far right is the 250. In all 3 cases, we see that the light gray bar reflects hyperexcitability in the hippocampal subregion relative to the control participants. So this has now been established in many different cohorts of MCI patients that this hyperexcitability is observed in the hippocampus. Both the 62.5 milligram and the 125 milligram dose significantly reduced that hyperactivity in the hippocampus, which was associated with an improvement in memory performance that depends on this circuitry. The 250 milligram dose did not have that benefit. As you can see, it did not lower the hyperexcitability in the hippocampus, and it also did not have a memory benefit. And I'm bringing the animal data back here, so on the far right-hand side, to show you how comparable these data are between the animal model and the human subjects, with these 2 doses being effective, but the highest dose being not effective. So, of course, the next step, in terms of testing this hypothesis, this study was successful, showing that the hyperexcitability is, in fact, not compensatory, but part of the problem. And it raises the question, obviously, does this work in a larger trial? Could we use this for symptomatic treatment in patients with mild cognitive impairment, as it is now recognized that in the amnestic mild cognitive impairment stage of Alzheimer's disease progression, in addition to having elevated amyloid levels, in addition to having tau, we see this increased hippocampal overactivity for a finite period of time in conjunction with hippocampal and cortical atrophy. So, going back, the HOPE for MCI study was designed. The HOPE stands for Hippocampal Overactivity Prevention in the Elderly. This was a phase 2B international site, showing the trial sites here across the United States and Canada that participated in this study. A total of 164 participants were enrolled in the study, and unfortunately this did occur over the pandemic with all the challenges that presented. The average age and gender are shown here on the left-hand side. We achieved almost a 20% minority or underrepresented minority participation in this study. But it is a largely non-Hispanic white population that participated in this study. All participants were amyloid positive as assessed by PET imaging, and the primary endpoint for this particular trial was the Clinical Dementia Rating Scale, which is a clinical cognitive assessment that's essentially used in all clinical trials of Alzheimer's disease. It was 18 months in duration. AGB 101 is a extended release version of low-dose levetiracetam. So in the initial study, we used BID treatments. We simplified that by making an extended release version of the medication, which is called AGB 101. Participants completed baseline amyloid and longitudinal tau, as well as longitudinal structural imaging. And I'm showing the results of the study here. And as you can see, the people in the primary endpoint analysis of the CDR sum of boxes on AGB 101 showed merely a modest, non-significant improvement compared to the placebo participants over the course of the 18-month trial, which was somewhat unexpected and obviously disappointing. However, in a pre-specified subgroup analysis based on our old friend ApoE, we did a subsequent follow-up analysis to look at the effect in those 2 subgroups. And on the right-hand bottom side, you can see that the effect in the overall sample was largely driven by the ApoE4 carriers who, as expected, made a overall sample. They showed a relative, again, this non-existing effect on the end of the trial. However, in the APOE4 non-carriers, you can see that there's a 40% benefit on the CDR Sum of Boxes score over 18 months treatment with AGB-101, lowering this hyperexcitability in the hippocampus, which is a very meaningful, although not significant, effect on the primary outcome of this particular study. We also, as I mentioned, collected MRI scans at baseline and at the end of study. I'm showing some preliminary data here from a study that we've previously completed showing the volume change or the shape change of the entorhinal cortex over a period of 24 months. From these studies, we know that there's a very specific pattern of atrophy in patients with mild cognitive impairment in the entorhinal cortex that shows clear progression over that time period. In the Hope for MCI study, we observed the following results. Those who were treated with AGB-101 that were in that non-carrier group that showed a 40% benefit on the primary endpoint of the CDR Sum of Boxes showed a statistically significant benefit of treatment on atrophy of the entorhinal cortex. So in the far left graph under A, you can see that the volume change in the placebo condition for non-carriers is approximately 6% change volume per year, over the course of the study, which is consistent with the literature. AGB-101 treatment reduces significantly so that volume change down to approximately 2% over the course of the 18 months. And in Brodmann area 35, which is sometimes referred to as the transentorhinal cortex, this was a trend towards significance in a similar reduction in atrophy as a consequence of AGB-101 treatment. So reducing the hyperexcitability here does have a benefit on clinical cognitive outcomes, and importantly so on atrophy in this entorhinal cortex region, which is critical to the progression of Alzheimer's disease dementia. These results are currently in preparation for publication. The prior results on the clinical cognitive outcome measure were very recently published in Alzheimer's and dementia. I'm going to bring you back now to this graph that I've shown before, noting the differences in successful aging and sort of impaired memory performance in these rats and the trajectory of the hippocampal overactivity. Now, this is, of course, a theoretical graph of proposed changes that happen over time. And you can note from the green line that there's a relatively early start of that hyperexcitability. And, of course, the key question is, when does this hippocampal hyperexcitability start? There's been evidence out there suggesting that this is not a condition that is specific to mild cognitive impairment, but that this condition can also be observed in aging individuals who are cognitively normal. So obviously the question arises, can we start with this treatment even before the onset of clinical symptoms? And can we ameliorate, can we reduce this hippocampal hyperexcitability? So to address this question, we engaged in a pilot study in collaboration with the University of Wisconsin, with Shizhang Li there at the University of Wisconsin, who was very interested in using functional connectivity imaging to quantify the functioning of the hippocampal network. Through the literature, we understand now that this change in overactivity and the excitatory-inhibitory balance in the hippocampus can also be observed in functional connectivity measures where it shows as increased functional connectivity of the hippocampus with the rest of the brain as a function of aging. This is from a paper by Salami et al. That I'm showing you on the left-hand side. So the increasing age is associated with increased functional connectivity with the hippocampus, with the rest of the brain. In this pilot study, a sample of 25 cognitively normal older adults were enrolled. Functional connectivity was used to quantify the functional connectivity of the hippocampus with the rest of the brain. And on the right-hand bar graph, you can see that compared to placebo, AGB-101 significantly reduced hippocampal connectivity with the rest of the brain in these cognitively normal older adult participants. So there's obviously a number of next steps that we have to consider going forward with this research. We're currently in the process of planning a phase 3 trial of AGB 101, testing the efficacy of this treatment in APOE4 non-carriers, obviously, as a successful treatment for MCI and MCI progression. We also need to understand more about this signal that we're seeing in aging. Can this be successfully used to slow progression of those who are on the path towards Alzheimer's disease by intervening early in this trajectory and selecting these cases for participation in these studies for early treatment? The third thing that we need to focus on is going back and essentially doing a back translation to the animal work to understand what the role of ApoE is in the effect of treatment that we're seeing here with AGB 101. And of course, the animal work can be hugely informative here in improving our understanding of the interaction between the treatment, hippocampal hyperexcitability, and ApoE4 carrier status, which clearly is very important as these data show. So with that, I'd like to thank the people in my lab and my collaborators that are making this work possible, and I welcome any questions.
So our speakers were all terrific at staying on time. So that means we have a little bit more time, which is great. So we'll jump right into general discussion. So I invite you all to come up to the microphones. And while people are kind of lining up here and taking their spots behind the microphone, I just wanted to get the panel started a little bit with something that Arnold mentioned, which is the idea of a trajectory. And I wanted to kind of know from you all, maybe we can kind of go round robin just very briefly. What does trajectory mean to you in your work? How do you define that? How do you think about it? Anyone can take it away. Nathan?
I'm happy to take it. I mean, to me, of course, trajectory is just the, mapping of health or the movement away from it over time. And it is what we focus on very strongly, obviously, in the digital twin models and so forth. I didn't show it, but what you're actually simulating is a trajectory of health through MCI, through Alzheimer's, through the avoidance of that, through brain health, through the death of neurons, but it's all basically time-based simulation. So,
Julie?
Yeah, so this is not necessarily relevant to the work I presented today, but I do a lot of work with older adults with anxiety and depression. And depression is definitely an episodic kind of illness where people are depressed at one time and not at others, whereas anxiety tends to arise early in life and continue through the life course. So I think kind of trajectories in those senses, what happens when people, kind of start out with anxiety and then how does that affect them in later life as opposed to people who might just develop depression for the first time later and have a potentially better outcome.
I think in what our data showed from our particular studies for clinical trials, we take enrollment criteria that person happens to meet at that point in time, and they get enrolled into an 18-month or a 24-month trial. And I think from our results, we can clearly see that those ApoE4 carriers were probably on a different path or a different trajectory or slope than the non-carriers were. And I don't think in general in clinical trials we keep that in mind enough, right? We have these enrollment criteria. We try to enroll as quickly as possible. We assume that means we have a uniform sample, but clearly we don't.
Go ahead,
Anne. One of the things I think about when I think about trajectories is thinking about the sequence of interventions, sort of generic case, but how different interventions applied at different times with different sequences can result in a different sort of health trajectory.
Okay, it looks like we've got lots of folks lined up at the microphones. We'll start over there, and we'll kind of go this way and just go multiple rounds. So let's start over here.
Thanks. Mitch Elkin from the American Heart Association. And another terrific session. Thank you all very much. Learned a lot. And I have several questions. I'll limit myself to two, if that's okay. The first one is, in the ACHIEVE and the MEDEX trials, I think the kind of one overall message was that the effects might be greater in people who are already experiencing more significant cognitive decline than in people earlier in the disease course. And I'm just wondering how we reconcile that with what we think to be the case generally, that, the further along you are, the less likely we are to be able to help people. And if we want to intervene in Alzheimer's disease or perhaps cognitive decline, we want to start earlier in life. We heard a lot about early or midlife interventions, how important those are. So I'm just trying to put those two pieces of information together. Do we just need much longer trials? Is that the only solution, or is it something else going on? I guess, Dr. Lin.
I'll take a first stab at it. So I think it's a great question. And I think as scientists who are dependent on 5-year funded grants, you're sort of limited in terms of the outcomes you can look at realistically. And that's a cynical way of viewing. Another way of viewing it, too, is like it's hard following go for 10, 20 years, and people want a earlier return on investment. Are they getting something out of it or not? So I think there's a pragmatic as well as a realistic thing is how quickly. I'll be honest, in the ACHIEVE trial, we were actually, if you pre-hoc, you would have think maybe the de novo cohort would do so much better because they're more likely to respond to hearing intervention, they're healthier, they actually use their hearing aids a bit more than the other cohort. And yet we found sort of the opposite. And that was really governed because, and I didn't show the data all, but like the de novo cohort, they actually use their hearing aids a bit more because they're super motivated to use the hearing aids. The ERA cohort actually use their hearing aids a little bit less. They use them too. But I think that effect was very much trumped, though, because the primary outcome was that ultimately reducing cognitive decline. In other words, you can't detect that unless you're going to have cognitive decline, right? So if anything, I think we're actually really encouraged in the ACHIEVE trial to see among the population, I shouldn't say really at increased risk. They actually represent more the random sample of the population, that we actually saw an effect there, even in late life, within just 3 years, right? And the thing I didn't get a chance to show, but all the other exploratory outcomes that would be very proximal to cognition, social isolation, loneliness, communication, even the brain MRI data, you're seeing clear signals there across both cohorts, right? Both de novo and ERIC. But it's only being manifested in reducing cognitive decline among the cohort that had a cognitive decline, I think. So, but I take to your point, though, that it is always an issue of a trade-off when you do clinical trials, though, of the study population. And if you get a population that's really healthy, that will respond better to intervention, you may not see an effect on the outcome, unless you're looking for a positive improvement, right? And the flip side, if you get a population with more risk, maybe they won't use intervention as well, right? It's this is really, I think, I hate to say it, I think it's more art than science a lot of times, because it's hard to model and predict completely. Yeah, I wish I had a better answer.
Yeah, with respect to MEDEX, I don't know whether we started too soon or too late, given that we were assessing these people, starting them when they were older, but they were healthier, so they were, potentially at a higher baseline. We don't have the data to say which is which, although, as I said, we are continuing to follow folks, so we will see. We will see what we will see.
Thanks. Could I ask a second question? So this is actually for Dr. Reinhart. I think it's really applicable to all of these different interventions and studies. But as I was thinking about your, direct brain stimulation paradigm and its effect on perhaps aging older people, I imagine maybe you've looked for effects on younger, healthy people to demonstrate an improvement, beyond normal. So we're not just talking about preventing decline, but actually making people smarter, having better memories and so forth, kind of cosmetic neurology, if you will. And so I'm wondering whether, what the equity implications are for those kind of treatments. Again, this is not specific to brain stimulation, but it kind of struck me most strongly there because it seems, you can get a long-term effect perhaps with a short stimulation, with the access to that kind of care might be for perfectly normal people seeking some advantage. Is that something you've considered?
Yeah, so one experiment that I didn't mention was we invited all the healthy young people from experiment 2 back into the lab and just tested the people, 4 couplers who had brain, rhythms that approximated that of the 60, 70, 80-year-olds. And so there was more room for improvement. So we were able to apply the personalized stimulation and see benefits in that subgroup. But actually, most of our work is in healthy young adults. It just does basic science, and we can see improvements there. But the improvements look largest in people with the greatest cognitive impairments, which kind of speaks to Julie's proposal in that other context. access and equity, and we don't think about that often. That's an important point. I get contacted a lot by like startups and industry folks to spin off technologies that would be available to the public, and they're already out there. These are devices that are easy to make yourself, potentially with So there's home hobbyists who are designing direct current stimulation, to my knowledge, with some tin foil and a battery and some wires. So I don't recommend that, but were things to progress through FDA approval through the regular kind of stages of clinical trials, and was it to become available like TMS is now since 2008 for MDD, then hopefully it would be available to everyone. Personally, more in the spirit of like Salk in the polio vaccine, let everyone have it for free. But yeah, it's kind of outside my core expertise.
Okay, let's move on to Aaron.
Thanks. Thanks. Yeah, Aaron Seitz from Northeastern's Brain Game Center for Mental Fitness and Wellbeing. And I'm kind of curious, and this is a follow-up of a question I asked yesterday on kind of validity and sensitivity of cognitive measures that are being used across these studies, because, each of the studies presented, we're using different cognitive measures. Some cases, there are practice effects that maybe makes it so that they're less predictive of people's everyday experiences. In other cases, people's everyday experiences might be changing, but we're not measuring them well. And I'm just kind of curious your thoughts about, this issue and, what might be needed to address it.
I can speak a little bit to that. Yeah, so in our first study, we did not find effects on cognitive control or executive function, and we thought that was probably because they were paper and pencil, and we thought some of these computer-based measures might be more sensitive. But, I don't think that was necessarily true. Something that I would be interested in for a future study would be kind of the equivalent of ecological momentary assessment, but, more frequent, things that come up on your phone, so that might kind of get rid of some of the noise and make some of these measures a little bit more sensitive. But we didn't do that.
Does other people have views on the same question?
Any other opinions from the panel on cognitive assessments? Sure.
I can just add to that from a clinical trial perspective. I agree more work needs to be done in that. It's very difficult to do that, though, right? If you're doing a clinical trial in the Alzheimer's disease space, you want to be able to compare your results with the others that are out there. So there's a threshold for changing something like that is very high. When you do a clinical trial, and there was several suggestions that we might need longer clinical trials, you need assessments that show progression over time, very reliably so. So that becomes very difficult to validate because you need to do long-term studies to be able to generate those types of data. So we need more work in all these areas, but they're difficult problems to solve sometimes.
Okay, let's go here.
Hi, Stan Colcom from the Nathan Klein. And my question is actually for Julie. It was an excellent presentation. I was really impressed with the study, very ambitious. The thing that really stuck out to me most, though, was the active control group, where you had this health education, targeted, asking people, the examples you gave were like improving their sleep, improving their diet, improving their weight. That, to me, struck me that you would be engaging those same physiological targets that you're trying to hit with the physical exercise, right? And so a priori, if you told me that you were going to do those 3 manipulations, I would not have been surprised that your education group didn't differ from your intervention group. Did you measure or report the changes in the physiological measures, the same like VO2 that you assessed in the fitness group that you did in the control group?
Yeah, we did, and we didn't find them, and we were pretty careful to draw a balance between people saying, I want to exercise more, and, they might have been walking a little bit more, versus the folks that were, enrolled in our trial where they had, in our case, they had membership in the YMCA. In St. Louis, they had access to, gym that was basically research oriented. And so I truly don't think that they were getting, even the folks who wanted to exercise more, I don't think we're getting the same amount of exercise in the health education group. But the challenge is, again, with behavioral trials is you need to get interventions that are comparably credible. And we had earlier in our study looked and seen that the health education and the MBSR were comparably credible. So if you get someone coming in saying, oh, I got the control group, this isn't going to help, likely it won't. So how do you find something that is equally believable but inert, so to speak? And also just for recruiting, you're able to offer something to everyone. I mean, these classes were clearly of value to people. People enjoyed them and I think got something out of them. Costs and benefits. But, I think I agree with you that we were not a lot of people were using exercise or doing different kinds of things that they were setting as goals, and not to the intensity level that we were bringing them along to with our intervention. That was the best we could do.
And just, I might have missed it, did you say you did collect physiological measures on the education group?
Yes, we did.
And they didn't move around?
No.
Nathan?
Yeah, I just want to make one follow-up point there. When we were building the digital twin models that I was talking about, one of the things that you get into is there was an expectation, right, that exercise would have a huge effect because of the importance of the perfusion of oxygen into the brain. The most detailed study of this, though, so one of the things that could happen is that exercise would change the slope of the trajectory in aging for how quickly oxygenation goes down in the brain. The most careful study of that, though, actually did not change the slope, but it was an offset, that it delayed the time of onset, but that the slope was the same after that. So one of the big surprises of the model was that when we then simulated with the most detailed data that was available, it actually predicted that exercise would have a pretty modest effect. Very surprisingly to me, I really hated that outcome. With the team. But anyway, just something that might be interesting to look at is, that is kind of when we looked at the whole thing, that was kind of what it came out. So it might be interesting.
Sorry, just as a public service, those models looking at the change in plasticity of the result from exercise don't really have anything to do with oxygenation. Right? The oxygenating of the brain it's pretty constant, right? So you don't necessarily see a greater amount of oxygen being delivered to the brain necessarily with exercise, right? It's really more like BDNF. These other mechanisms that change the plasticity and improve performance over time. There's kind of a folk idea that you're just getting more oxygen to the brain is necessarily beneficial, and that's generally not the case.
We just take the exact measures that are done, so that's what goes in.
Just make sure.
All right, moving on to Jen.
So my question is for Dr. Lin. I'm really glad you're here because the ACHIEVE trial has really fundamentally changed what I think is possible about trials to improve cognition. So the first thing is really just a comment. You described the ERIC cohort as a random population sample, but they were random in 1987 when they were recruited. What they were when you started your trial is something that is based on a random sample from those cities, but it's not now. So that's just a comment, I think, just for accuracy. The other part is, I'll be honest with everybody, I really don't understand. I'm having a hard time understanding this issue with practice effects versus the population decline more, right? So I understand what you're saying, that ERIC cohort was tested over several times, and as a result, the tests that were used in the trial were not particularly novel for them, and so you didn't see necessarily that bump up. But I'm wondering if you can say more about the trajectories within each group, if you took a look at that, if you can help us understand how much of this is practice effect, or how much of it is the very important conclusion that you came to, which is that people who are essentially at higher risk for cognitive decline are the ones where we should be, focusing our trials. And then I have one more thing, which I have to look at my phone to remember, because I'm getting so excited. I'm sort of fangirling here because I've been talking about your trial for a very long time, which is you, at the very end and in your answer to Mitch, you kind of mentioned the real movers, which were the social isolation decline and the well-being increase in the people who were randomized to the hearing aid. Is it possible that the effects of hearing aid were indirect through those social / well-being mechanisms and not through hearing in and of, hearing in and of itself?
So, John, thank you so much for those phenomenal questions, and I completely agree, by the way. So Eric they were a random sample 30 years ago, followed present day, and sometimes I just verbal slip, but they represent at one point a random sample that's still been followed to the present day, and they're the survivors of that, but also the new healthy volunteers are also survivors of the cohort years ago too, trajectory question first, in terms of that. So practice effects. Yeah. So this is really, really interesting. So the data that I showed you today, which is what we present in the Lancet trial, is all predicated on baseline and year 3, and not using any of the intervening data, which is not what we intended to do. We intended, if we had modeled, and people, Alden Gross and people who work with us, we intended to model the trajectories per se using year 1, year 2 data. The reason why we had to throw that in the end, though, was because the year 1, year 2 data, some of it was in person, some was on the phone, and the phone-based neurocog, it's a mess. I mean, that's just very different. You can try, and we tried renormalizing it because we had some people who had both, but in the end, it was decided by the DSMB and RCP that we'd only use baseline in year 3, just to make it a clean analysis we know we got. That being said, though, what we had always planned for is these sub-analyses, though, that if we hadn't had missing 1 year data in person, is you can, and we actually did, you can model prax effects, and it doesn't affect the analysis in terms of do you see a bump up and things like that. What we haven't done yet, which is on the laundry list of things to do, though, is actually look from people who, you're taking a selective cohort, people who actually had year 1 in person, for instance, right? And there's a lot of people who did year 1 in person, is do you see more of a prax effect among the de novos versus Eric, and actually do you see an improvement per se, less you did Eric? I would say, a priori, we think we would see less of a bump Eric's, but that's actually we can empirically test. We just haven't gone around to it. But that's why for the main analysis, we only based on year 3, just to make it a clean, internally valid study, though. Otherwise, normally we'd have accounted for that even better, but we just didn't have complete year 1, year 2 in-person data. Your other question about, I think really gets at mechanisms. So if we believe these effects, the hearing intervention is having a positive effect on reducing cognitive decline, how? Why? And I think it comes up with mechanisms again, the idea of cognitive load, effects on brain structure function, and or social function, or social isolation. I think it's not going to be one. It's kind of like a combination of all 3. I showed you some of this preliminary data today on the brain MRI data, which, again, I shouldn't say this because it got funded by NIH grant. We didn't think we see anything, right? Because this is 3 years, but we saw a signal there which is intriguing, right? That maybe it really is operating through reduced cortical thinning atrophy over 3 years. But at the same time, too, though, and again, I didn't show it, but all the other exploratory outcomes, specifically loneliness, Cohen social network, SF36, communication, you're either seeing improvements with hearing intervention and or, again, relatively reduced declines. So another thing in the list of analyses to come are the formal mediation analyses, right, with structural equation modeling, which are on the books. That's actually, Alden Gross will be doing those with us in terms of actually looking at mediation modeling. We just haven't gone around to it yet, though. We will, though. So,
isn't it possible that the brain imaging findings, the cortical thickness findings, could also be explained by the improvement in social interaction and well-being?
Yeah, no, absolutely. Okay. The only thing there which is interesting, though, and again, I'll frankly say it's hand-waving because we went into this sort of as exploratory analysis. One of the strongest signals on the MRI scan so far, which I just touched on, was the pars orbitalis, right? Pars orbitalis is critical for language processing. So it appears it's more of a specific effect. And I'll digress really quickly. If you look at previous observational data looking at hearing and brain structure function, where you're seeing the biggest effect usually of observation of hearing loss and brain structural atrophy is actually the lateral temporal lobe, right? In terms of accelerated atrophy with people with hearing loss. I don't know if you remember from the slide, though, you're seeing the smallest effect in the temporal lobe with hearing intervention, which, again, hand waving might make sense, though. Hearing intervention is not reversing hearing loss, right? You're actually, well, it's not at all. It's really there. So in a way, it makes sense you're seeing positive effects in other regions, not actually the areas which can trophically be affected by actually auditory deprivation. But again, Jen, I got to tell you, it's just early days, I think, in terms of analyses. So I think all hypotheses are on the table still, and we'll get around to it. Thank you.
Okay, let's go to the corner here.
Can you hear me? Yes. I'm Moïse Devarieux, Columbia University, Medical Center. I'm a multi-morbidity epidemiologist. I'm fascinated by the talk, that's what you guys have found. I have two quick questions. One is regarding the AD biomarkers, for example, that we talked about. The high level in the context of comorbidity and multimorbidity, are you suggesting that it's related to actual production? Seems to be that is different, but it may be also, especially in the context of EGFR, it can be the question of clearance. And I'm having a hard time having that conclusion without having other non-AD biomarkers as controls. So that's one thing in terms of thinking. And the second question is related to the great trials that were presented, for example, the SHIFT trial and the ERIC. I want to follow up on what Jennifer was saying for the ERIC study, but the population of African American in Jacksonville, as you said, was really hard. I think one was in Minnesota, was just the opposite, and the other one was at UAB, I think. I can't remember where the fourth one was. So in the new cohort, did you stratify? I might have missed that when you presented. Did you stratify by source population in terms of enrollment in the new cohort? Because that could have, so that's my first question. Alleviating possibly the imbalance. And have you perhaps tried to also analyze by site? And following up on Jennifer's question, for the trajectory, because in ERIC at Jacksonville, you will know the trajectory of hearing loss. You will not, because you will have previous. So will that trajectory, how do people get there, impact? And the last one sentence, and I know that's the last one, and it's something just as an epidemiologist that I have to say, the beautiful work that was presented about the trial, which was result was that there was no result. It's not a negative trial, you know. It's a result. You know that, but I'm just saying, and it may allow you to actually identify subpopulations that are actually just like not underestimating your work. So, yeah,
yes.
I thought to ask questions.
I'll answer very briefly. I'm happy to talk to you maybe after you get a lot of questions. So I will just say, so briefly, again, I think what you're highlighting is the ERIC cohort was recruited 30 years ago, 16,000 people roughly. The Jacksonville study was specifically designed from the very get-go to be 100% Black American. That's why all of Jackson's Black. Other sites actually predominantly white in terms of where they're based. Minneapolis suburbs, very much rural Western Maryland, and Forsyth County, Wake Forest was a bit more mixed. So that's why in the ERIC, the breakdown of racial ethnic, it's a little different because of that original design. The de novos were recruited from the same communities, the exact same 4 communities. But there, you're not nearly seeing the same degree of racial diversity, I think, a lot, because these are healthy volunteers, and those are people usually, people who came in to study that way. So it was not specifically meant to be stratified or another. We sort of took all comers. Your question, I'll answer really briefly. A lot of the subgroup analysis you're getting at, if we do subgroup analyses by site, by sex, by race, education, things like that, we didn't really see anything yet. I mean, there's no smoking gun per se. Every time you subdivide a little bit, it's always like, how do you interpret it? But we're certainly not seeing any smoking guns per se in terms of, should I say smoking gun, but in terms of very strong signals with any type of the subgroup analysis. The one we thought we see one is actually divided by severity of hearing loss. People with more of a moderate, greater severity, with a mild, you see more of a signal there. We're actually not really seeing any strong differences. Maybe some trends, but nothing clearly to write home about. That is a whole separate paper working on all this different subgroup analysis that were pre-specified. We haven't published that yet either. But I can tell you the preliminary readout is that it's you're not seeing any big differences by sex, by level of hearing, education, or anything like that either. Yeah, I don't think we actually have looked within study sites, but we certainly could by all means. Just your sample size gets more and more constricted the more and more you do that, though, of course. Yeah. Thank you. But happy to chat later afterwards. Yep.
All right, Gina.
I have a question for every single one of you, but I'm going to ask the one question that sort of encompasses most of you. And I'm asking it because I'm never done human studies before, and I'm about to do a survey of sleep in South LA, and I'm deathly afraid that I'll be wasting my time because the only ones that will volunteer for my study will be the affluent ones who have the time and I will not get a survey of sleep in South LA. So how can we do better at really actually sampling the population so that we get people who really might benefit from the interventions? People might, I feel like we could waste millions and millions of dollars and years of time if we don't get the right population. I'm asking all of you in the room, how can we do better? I mean, we know a lot of the problems of community engagement with populations. People don't come forward, and it's either because they don't trust us, which they shouldn't, or maybe they should trust us, but they don't know that. We don't communicate with them. They don't tell them the results of the study afterward. We don't give them anything back except a gift card or whatever it is that, and they don't have the time, and they're too engaged. How do we do better? Anybody? Please.
Well, you're asking someone who wishes they had done better. I know that people have, and we tried some of this, people have tried recruiting through organizations with, kind of trusted gatekeepers, if you will. So if you involve, for example, religious figures, ministers, pastors, kind of at the beginning even of your planning stages, and then you might have a little bit better luck in kind of being seen as a safe and trusted source of assistance. We presented at a lot of health fairs, and some of those were targeting specific populations. I think this means you're not going to get a random sample, but I think asking people to refer their friends and neighbors, what in sort of getting completely random, which you're not going to get for an interview. I mean, of course, you said a survey, so you might want a little bit more random.
Yeah, well, even if you do phone calls, the only people who are answering their phones are the ones that are home and don't have 3 jobs. And so, I mean, it just seems, and to build those community trust partnerships takes years. And I'm sure these church leaders are getting lots and lots of requests now
So, Gina, I think in some ways you answered your own question by saying, here's all the stuff that we just do the opposite of all of that, right? Because clearly that hasn't worked. Yeah. We were having a conversation earlier. I don't know if Jen is still here, but we were having a conversation earlier. There she is. Do you want to weigh in on this? Do you want to weigh in on this? Okay, fine. I'm channeling Dr. Manley here. But I think it does take a very carefully thought out approach and real partnerships with the community. So organizations is part of it, but also listening, going out into the community and just spending some time not asking for anything and just trying to understand the challenges, to understand what they're going through, then trying to build those partnerships.
Can I say that on the listening standpoint, I also fear that the questions I'm going to ask with my ecological momentary assessments aren't the ones that are relevant, all right? I mean, they are very limiting. I want to do 3 1-minute samples in a day, but maybe I'm not asking the right questions. Maybe I need to actually listen to the community and see what the right questions are before I fill out this survey, or give them a free form area that they can tell me what is, the problem, rather than me assuming what it is.
All right, Jen is here to answer your question.
I just want to say I'm so glad that you're sort of outing yourself as being at this stage, because there's going to be a lot of people in the room who are thinking the exact same thing as you are. And I think that, first of all, there are people in the world who have expertise in this type of thing, and I would urge you to partner with them in a meaningful way, because they have had success and they have trust and they know the science of inclusion, which is what you're talking about. And what they're going to do is community engaged methods, so that those questions that you have, if I were to ask you these questions about sleep, how would that come across to you? Yeah. That sort of cognitive interviewing type of thing is one approach. Yeah. You could partner with the community to really come up with the questions. People do that as well. There's a lot of options, but they're, generally, and it takes a lot of resources. It does take time, but it's time and resources that should be built into any study. That is what we should be expecting from studies that are seeking community, participation and representative participation. So that's just a start. Okay, thanks.
Thank you, Jen. I will just add maybe just one more thing, very, very briefly, because I don't want to take up too much space here. But one of the problems that we deal with is actually structural in the way that our grants and our projects are designed, right? So we design our research questions. We think those are the most important questions. And then we say we're going to go out into the community and collect the data. But we're missing that you just talked about, which is really co-designing the research program and the questions with the community, asking the right questions, being informed by what they have to say. Right. And I just don't think we do enough of that. But that's what we learn about in CBPR as well. Right?
Even the IRB wants the full survey of questions before you even submit it,
But it doesn't hurt to just go out and chat.
Yeah.
Right? I don't think you need IRB to sit down and have a coffee conversation.
Good. Thank you.
Okay.
Joel Salinas with the American Academy of Neurology Brain Health Initiative. To build off of Dr. Poe's very important question, I wanted to ask Dr. Lin, but open to anybody on the panel. Given the 90% retention over 3 years is very impressive, what were any learnings that you had in that process that might explain why it was so successful?
Yeah, so a couple of thoughts there. The ERIC field site staff, which has been together for 30 years, is just a phenomenal group of professionals, right? So there's that aspect of it. And what I mean by that is they've retained the ERIC participants for 30 years, and a lot of that was really a lot of TLC and hand-holding. They send birthday cards and thank you cards. We arrange for transportation. Someone can't drive in. We send a car to pick them up to bring them to the field sites. We do home visits. We have to. So there's that structural type of stuff, which is super important. Beyond that, too, I think another thing about the study design, too, was that you're always getting something. You got the hearing intervention or the health education control was positioned as, and really is a real program. It's called the 10 Key Successful Aging. It's a real program that they're getting one-on-one hand-holding with a nurse, with a health educator, usually a nurse. So there's a lot of, everybody got something, right? So I think there's something in it, what's in it for me, for the participant. There really was something in it for them. And we said, too, after 3 years, you also get the other intervention as well. So I think it's a combination of the study design. I think the actual interventions were appealing to people, first of all, right? And then I got more of the others. It's really a credit to the study staff that have been together for many, many, many years with a very high degree of professionalism about how they treat these participants the way they would want to be treated or the way they should be treated, I think. Yeah. I wish there was a magical element beyond that, but I think it's really just a lot of little things that matter there.
Thank you. Okay, let's go here.
Hi, I'm Kamalini Ranasinghe from UCSF Memory and Aging Center, and my question is to Dr. Bakker. This is about the Hope for MCI trial. I wonder whether it's very informative about the stratification of ApoE4 carriers versus non-carriers. I wonder whether there was any quantification of hippocampal hyperexcitability in this study participants, like electrophysiology or fMRI, and whether would it be the case that if you stratify these participants with individuals who have hyperexcitability versus who don't, or who are at the high extreme of it, or against the lower extreme of it, would that be beneficial in the people who have this or who are at the high extreme of that?
That's a great question. And so in the Hope for MCI trial, there was structural imaging, but there was not functional imaging. It's very difficult to aggregate functional MRI, and particularly the high-resolution fMRI that is necessary to localize this hyperactivity to hippocampal subregion or even the hippocampus overall is very challenging to aggregate across trial sites. The additional complication is that it limits the trial sites where you can implement your study, creating a further bias in your sample selection. So the choice was made to not include that. We did collect this particular data on the subset of participants that completed the study at Johns Hopkins, obviously, because we did that at a single site, but there's not enough subjects there available to do that breakdown between the carriers and the non-carriers. It wasn't planned for. So we're looking into that now, going back to all the historical data that we've collected where we have this fMRI data, trying to understand what the source of those differences might be. In answer to your question about can you look at an individual subject's hyperexcitability, these are measures that are obtained at the group level, and they're very small signals that you can get at the group level. And unfortunately, it's not possible to identify an individual subject as having hippocampal hyperactivity or not having hippocampal hyperactivity, because there's no baseline to compare that against, right? There's no threshold that we can say this person is positive or negative. So we need to find solutions to that problem. I'm obviously very interested in solving that problem. And that's something we're going to focus on going forward.
Thank you.
Sure. Okay, we've only got a couple minutes left, so this is like the bonus round. We're going to go quick questions, quick answers, right? Go ahead.
Ron Lazar from the UAB McKnight Brain Institute. A comment on a comment that someone mentioned that oxygenation really doesn't have an impact from exercise. I could not agree more, because if you haven't exceeded something about cerebral autoregulation, oxygen ejection fraction, you can pump all the oxygen in the world and the brain couldn't care less. The question I wanted to ask Julie was, you mentioned you found 70% adherence, but it didn't tell you anything about the quality of the exercise, because if you don't do high-intensity exercise based on our data, you don't get a treatment effect.
That's true. The only proof we have is when we assessed folks and we found that they had improved in various things like their strength and their fitness and their insulin sensitive of things. But you're right, we didn't have a sense day to day exactly what they were doing.
Because in some of the studies we've done, we've found big differences in VO2 max, but nothing else.
Okay, let's go here.
Hi. I'm a physician and I also teach mindfulness and fitness. So I was just curious to know, in the control group, was it assessed their mindfulness before, after, and also how did they live their life, their lifestyle? What kind of stressors do they have in their life? I'd be curious to know, compared to the experimental group, like kind of other stressors they had in their life.
Right. So all groups, we use the CAMS-R to assess mindfulness across all of our all the participants. In terms of kind of stressors, we did not assess for life stressors, which I think is a gap in the data that we collected. And in terms of their sort of overall lifestyle, there was a suggestion at one point to ask about diet and, kind of some other factors. But again, we were already, kind of collecting a lot of data from folks. So that was one of the things that we did not do. In the extension, which has gone through the pandemic, we've been asking about stressors. So we're looking at social isolation and loneliness and some of those things as well. So the extension is more of are these things protective against stress, and does that have an impact on cognitive function? But in this first phase, unfortunately, no.
Okay, and their level of mindfulness before and after in the control group?
The CAMS-R.
Okay,
yeah.
Okay, I'm getting a signal that we have to shut it off here, but this was a great discussion. Let's thank our speakers one more time. And Molly, you're up.
So we're at the end of the meeting, and I always like to see or gauge at a level of success of conferences like this in terms of how many ideas we've seen that are going to be turned in or have been turned into actions or research, and then taking those actions into implementation. So over the past couple of days, I've heard a lot of encouraging talk that we are moving in the right direction, in the kind of directions that we want to move in, to begin to really sort of pierce the envelope and move forward in a very positive and different way, and instead of doing what we've been doing, but to improve and try out new opportunities, new approaches, new technologies to really further our knowledge. So I would like to recognize again the speakers. Their efforts and contributions have been even more extensive than the sharing of the important research findings over the last couple of days. They've been working with NIA staff for weeks, months even, via pre-meeting discussions, development of content for their talks, and consideration of gaps and opportunities for this scientific space. efforts for which they have generously given their time and insights. So one more round of applause for our speakers. Those we don't see but who allow us to see and hear everything, my deep thanks goes to NIH Events Management. That's David Higgins and David Chang, who are over on the side of the room. From the Bethesda North Marriott Hotel here, Hector Lopez. From NIA, a person who hasn't been with us but who has been working in the background over a number of weeks, Dwayne Diggs, and Raul Narne. Whenever I see Raul, an instant wave of calm and confidence sweeps over me. So thank you very much, all of you who have helped us see and hear the conference. From FNIH, we've worked closely over, again, a number of weeks and months with Matt Slater, who is the Director of Corporate and Foundation Relations, and have appreciated his guidance and presence throughout the lead up to the summit. And then, of course, there's the FNIH event staff who have coordinated all the logistics to bring us here for the past 2 days. That includes Mira Patel, who is the Director of Meeting and Events, Rakia Hicks, Jasmine Buchanan, and the prime mover. I'm not sure if she's in the room. I had asked the staff to come into the room, but I don't know if she's here. There she is. For all summit-related logistics, Ashley Spunnigal. A meeting of this caliber and scale takes enormous commitment, effort, and skill, and this team brought all three to the table to make this happen. So our thanks to FNIH. Not present, you haven't seen them, but they did a lot for working up to this day. I still want to recognize from NIA, from our Office of Communications and Public Liaison, Jordan Broderick and Kelly O'Haver, who helped NIA advertise this summit through the creation of a meeting website and other communication and dissemination efforts. And then I want to have special thanks to the members of the Summit Organizing Committee, who also served as the session chairs, if you didn't notice that. Their contributions also have been enormous, and they've generously contributed their time and expertise over a number of months, and through today, and through our executive session that will be this afternoon. And that's Dr. Carol Barnes, Dr. Jen Bison, Dr. Randy Buckner, Dr. Catherine Kazarowski, Dr. Jen Manley, and Dr. Saul Valeda. So thank you. And then there's the NIA folks, more of us. So I want to thank Dr. John King and Dr. Aaron Harrell from the Division of Behavioral and Social Research, Dr. Dave Frankowski from the Division of Neuroscience. They rose to the occasion more times than you would care to count to make this summit the cohesive, exciting, bleeding edge, and impactful event that it's been. And so I'm going to ask them to rise one more time so that we can recognize their central role. John and Aaron and Dave, you could stand. And I'm going to take a moment to individually recognize Dave Frankowski, who cheerfully and consistently offered his skills and time to every aspect of the planning and execution of the summit. Thanks, Dave. But most importantly, our thanks goes to the McKnight Brain Research Foundation Board of Trustees for having the determination, the commitment, and the vision to prioritize cognitive and brain health. This marks the fourth time the foundation has made it possible to convene this very important meeting. Angelica Schlanger, the executive director for the foundation, worked closely with the Summit Planning Committee over the past several months and provided valuable input and resources. And during the planning phase, Trustee Dr. Amata Thambasetti and Chair of the Board, Dr. Mike Dockery, met with us multiple times to help guide us on the content and direction of this. All here today because of the McKnight Brain Research Foundation. Thank you.
time, I'll turn it over to you, Mark.
Well, thank you all very much, not only for sticking it out to the end, but for being here in the first place. I'm amazed at the distances that people have traveled and taking time out of your schedules, not only to be here, but particularly the organizing committee, giving us some wonderful new ideas that are new to me. So I thank you for that. Let's see, I do want to have a few public relations comments here. You can take a picture of that if you want. The new BrainWorks site goes live tomorrow, and we're wanting that to be an outreach. So share that with friends, family, patients. And then also on our website, while you're there, we have several partnerships where there are funding opportunities. So I know that always piques the interest for folks doing research. So be sure to check that out as well. And then I guess here at the end, I would really just thank you all again for the great research. I would kind of ask for a little twist, because we're looking for how can we make a difference. So then the question always is, how can we apply this clinically in humans to make a difference, to help us successfully age well? And so as long as we have that lens through which we're viewing everything, I think then the work makes an even greater significance. So thank you all again, and I think that's it.
And that concludes the meeting. Safe travels home, everyone. Thanks again.